Hello there, and welcome to Science for Sleep, where curiosity settles quietly beside you, and the universe unwinds itself in slow, steady explanations that leave a little more room for rest. Tonight, we're easing ourselves into one of the strangest frontiers ever proposed in science, a threshold where the rules you and I depend on for everyday life begin to shift. It's the edge of a black hole, that boundary known as the event horizon, a place that has held the attention of scientists, dreamers, artists, and anyone who has ever looked up at the night sky and wondered how far reality can stretch before it starts behaving in ways that no longer match our expectations. This spot in the universe is not loud or dramatic in the way many illustrations make it seem. In truth, it's quiet, steady, and incredibly patient. With all the seriousness of physics behind it, the event horizon doesn't make noise or flash warnings. It just exists as a gentle marker between where light can escape and where it cannot. A kind of invisible line hanging in space. Important not because of what it looks like, but because of what it means. We hear so much about it as a point of no return, and that's true, but it's not a wall. It's not a surface you can touch. It's more like a place where something familiar in the universe changes its mind. Before we go there, I'd like to ask you something simple. Where are you listening from tonight? Are you somewhere winding down after a long day, or maybe settling into bed as the room gets dimmer and quieter around you? Whatever the time is in your part of the world, it's just the right time to soften the edges of your thoughts and follow along at an unhurried pace. These explorations are meant to be gentle. You don't need any background in astronomy or physics. All you need is the curiosity you already have. If this kind of slow, relaxing journey through science brings you comfort or helps you unwind, I'd be grateful if you gave the video a like or subscribed. It helps this small corner of calm find others who might need a little space to breathe, think, and drift. So, let's begin by easing toward this idea. Imagining the edge of a black hole might feel intimidating because of how often it appears in movies and dramatic artwork. It is usually drawn as a swirling spiral of doom, a kind of cosmic drain sucking everything toward it. But the truth is much steadier. If you replace the Sun with a black hole of exactly the same mass, Earth would keep orbiting just as it does now, without falling in or spiraling away. There wouldn't be a sudden pull or a visual spectacle. From our distance, you wouldn't even notice anything had changed. That's how calm black holes actually are unless you approach them closely, and we're only doing that in thought, moving step by step at a pace slow enough to let the details settle. Black holes begin as stars, enormous ones that run through every drop of fuel they have. Once they burn through it all, they collapse under their own weight. Gravity, which is the same thing holding you to your chair or bed at this moment, pulls the star inward with such strength that it compresses everything into a region so dense that nothing, not even light, can climb back out. This collapse creates a gravitational field so extreme that it forms a boundary. That boundary is the event horizon. Inside it, escape becomes impossible, not because something is actively grabbing or pulling with extra strength, but because the shape of spacetime curves so sharply inward that all possible paths lead deeper instead of outward. It's like standing in a valley that has no upward slopes left, only downward ones, no matter which direction you choose. Picture it this way. Imagine you're standing on a hillside. You can walk in many directions. Some lead up, some lead down, some go sideways. This is how the universe normally behaves. Now imagine a place where every direction you look slopes downward, even behind you. That's a little like the geometry near an event horizon. It's not something you can see with your eyes, but something that affects the path everything must follow. This is what makes the event horizon important. Not the appearance, because it doesn't glow or ripple, but the behavior of space around it. It's a place defined entirely by what light can or cannot do. As we drift mentally toward that boundary, we can think about light for a moment. Light is fast, the fastest thing in the universe. It travels at about 300,000 kilometers per second. That's quick enough to go around Earth more than 7 times in a single second. Rapid enough to escape almost anything except a black hole. When you get close to the event horizon, the pull of gravity is so steep that even something moving at light speed finds no path leading outward. This isn't because the black hole snatches the light, but because the routes available in spacetime all point inward. Light simply can't pick a direction that allows it to leave. Once you cross that boundary, no path takes you back. That's why the event horizon matters. It's the separation between where things can send signals outward and where they cannot. Now, gently, we can think about what this means for someone falling inward. Not in a frightening way, but in the curious, careful way that scientists study such things. If you drifted toward a very large black hole, one far bigger than anything found in our everyday sky, you wouldn't feel much different as you reach the edge. At least not right away. Your body doesn't sense changes in time or curvature of spacetime directly. You wouldn't notice yourself crossing any border. There wouldn't be a sound or a flash. The event horizon isn't a physical surface. It's simply the point beyond which light fails to escape. So you would pass through without anything announcing it. If you could send a message outward, it wouldn't reach anyone after that point, but nothing would warn you of it. Things feel normal to the one falling in, which is one of the most unusual and counterintuitive aspects of black holes. Outside observers, though, see something entirely different. As you fall closer, your movements appear to slow, your image becomes stretched. Light from you gets redder and dimmer. Eventually you seem to freeze in place right at the edge, fading slowly until you disappear. This isn't because you actually freeze, but because time itself bends differently for you than it does for someone watching. Their perception of your time gets stretched out in a way that looks almost like the universe pressing a pause button. But from your point of view, things continue steadily, without the sense that anything peculiar is happening. In a way, this difference in perspective is part of what makes the event horizon such a compelling place to explore. It's a boundary where time behaves differently for different observers. It's like having two clocks that don't agree on how long a second lasts, even though both are ticking correctly in their own experiences. Time close to a black hole passes differently. The deeper you go into its gravitational field, the slower time moves relative to the outside world. This isn't a trick or an illusion. It's something that has been measured, tested, and used to confirm Einstein's predictions about how gravity and time influence each other. Even here on Earth, clocks on satellites tick slightly faster than clocks on the ground, because Earth's gravity is weaker at that height. Engineers must correct for that difference to make GPS work. Extend that effect to something as massive as a black hole, and the change becomes far more dramatic. That's why your fall seems to slow in the eyes of a distant observer. Their clock and your clock are disagreeing more and more as you approach the event horizon. As we move further in thought, we can imagine this edge not as a danger, but as a boundary of understanding. For decades, scientists have worked to determine what happens at this threshold. What kinds of information can pass through? What happens to objects that cross it? How do the rules of physics behave when pushed to their extremes? These questions aren't just academic riddles. They sit at the centre of some of the deepest puzzles in modern physics. The nature of gravity, the behaviour of quantum particles, the relationship between space and time, and the structure of the universe itself all converge in surprising ways at this boundary. In a sense, the event horizon is where physics raises an eyebrow and asks, "Are you sure you know how the world works?" It's not a place filled with chaos, but with careful challenge. It forces scientists to test whether their theories are complete, or whether something important is missing. Before moving deeper, we can take a moment to settle in. There's no rush. This journey isn't a chase or a dramatic drop. It's more like standing near a quiet lake and watching the surface reflect subtle ripples. There's a calm in considering something so far away, so removed from daily concerns, even though it reaches into ideas that shape how we think about the nature of everything. That's part of why these late-night explorations work well for gently softening the mind. Thinking about something vast and steady has a way of loosening the tight grip of everyday details. It gives you permission to let your thoughts slow, not by forcing them to stop, but by offering something larger and quieter to think about. The The event horizon is often described as a point of no return, and that phrase carries a lot of weight. But no return isn't about danger in the usual sense, it's about information and communication. Once something crosses the event horizon, no signals, no light, no messages can escape. The outside universe has no way of knowing what happens inside. This is what creates the mystery, because physics normally expects information to be conserved. If you burn a piece of paper, the information about that paper still exists in the smoke, the ashes, the heat released. But in a black hole, the information seems to vanish, trapped behind the event horizon. Scientists have debated for decades whether that information is truly lost, or whether it's stored in some way on the event horizon's surface, or even released slowly through subtle processes like Hawking radiation. These questions make the event horizon not just a boundary in space, but also a boundary in knowledge. None of this requires rushing or worrying. Thinking about it slowly lets each piece settle at its own pace. You don't need to grasp all the details at once. Just the idea that the universe, even in its most extreme states, follows rules. They may be unusual to us, but they are consistent. Black holes are not chaotic monsters. They are stable, predictable structures, defined clearly by mass, rotation, and charge. Their boundaries don't flicker or change opinion. They remain steady in the darkness. The event horizon can seem intimidating from a distance, but approached gently, it becomes simply another part of the universe, another phenomenon that follows rules and patterns. In the same way that sunsets, tides, and moon phases have their rhythm, a black hole has its own behavior guided by physics that, while extreme, remains understandable when taken step by step. When we start tracing the origins of something as extreme as a black hole, it helps to settle into the idea that nothing about its formation happens suddenly. There are no abrupt shifts or violent cinematic explosions that match the way movies often frame these objects. Instead, the beginning of a black hole emerges from the slow, predictable evolution of a star that has lived a long and heavy life. Stars are not all the same. Some are small and steady, content to burn gently for billions of years. Others are massive, burning through their fuel far too quickly, because their own weight pushes their cores to produce energy at a faster and faster rate. The ones that eventually become black holes belong to that second group. They are giants by comparison, carrying enough mass that their behavior begins to differ from what we see in ordinary starlight. To follow this path, imagine a star many times heavier than our Sun. Throughout its life, it fuses elements in its core, beginning with hydrogen, the simplest and most abundant element in the universe. Fusion is the process that keeps stars shining. It pushes outward with energy that balances the inward pull of gravity. For a long time, this balance holds securely, but massive stars consume their fuel quickly. They generate so much heat and light that they run through their hydrogen supply faster than smaller stars. When the hydrogen runs low, the core contracts, becoming hotter and denser, and this new compression begins fusing helium into heavier elements. This pattern continues as the star ages. It keeps creating heavier and heavier elements, each stage happening more quickly than the last until eventually it reaches iron. Iron is different. Fusing iron does not produce net energy, it consumes it, and that fact marks the beginning of the end for our massive star. Without a new source of outward pressure, the core loses its counterbalance. Gravity starts to win. When that inward pull no longer meets resistance, the core collapses. This collapse happens quickly, but not in a way that breaks the laws of physics. It simply follows them to their most extreme conclusion. The outer layers of the star rush inward, hit the compacted core and rebound. This rebound creates a supernova, a bright and powerful explosion that can outshine entire galaxies for a short time. Most of what we see in pictures of stellar debris, rings, filaments, glowing clouds, comes from these explosions. But the core, the very heart of the star, continues collapsing. If the star was massive enough, the collapse goes beyond forming a neutron star. Instead, gravity compresses the core into a region so dense that even atomic particles can no longer maintain their separation. At that moment, the core forms a singularity, the central point of infinite density at the centre of a black hole. The singularity itself is not something we can observe directly. No existing tool or measurement can reveal what it looks like or how it behaves. But its gravitational influence is unmistakable. The space around it becomes curved in a very specific way. This curvature defines the presence of a black hole and creates the boundary we recognize as the event horizon. The horizon marks the radius where escape velocity equals the speed of light. Outside that boundary, light can still outrun gravity. Inside it, nothing can. This shift from a collapsing star to a black hole is not visible from the outside. The supernova may be brilliant, but the formation of the event horizon is silent. It does not display a flash, a ripple, or an outward signal. The material collapses inward and the boundary appears, sustained entirely by gravitational geometry rather than any physical surface. Everything about it is stable, precise, and determined by the mass remaining in the core. The birth of a black hole is not rare in cosmic terms. The universe is vast enough that massive stars reach the end of their lives regularly. Each collapse leaves behind a region where gravity becomes so strong that space itself bends dramatically. Yet each one follows the same rules. Gravity is the architect, the star's mass is the material, and the result is an object defined not by chaos, but by consistency. This process has been studied for decades, and although there are still open questions, the overall framework is solid enough that scientists can describe the formation of a black hole with confidence. To understand this more comfortably, it helps to picture the forces involved. Gravity is a familiar companion, but it behaves differently depending on how much mass is present. Here on Earth, gravity shapes our everyday experience. It gives weight to objects, keeps the atmosphere attached to the planet, and makes dropped items fall. In the Sun, gravity compresses millions of tons of gas, creating the conditions for fusion. In the core of a massive star nearing collapse, gravity becomes even more pronounced, pressing matter into densities far beyond anything Earth can produce. As the star runs out of fuel and the outward pressure fades, gravity takes full command. It's not aggressive, it's simply persistent. With nothing left to resist it, the collapse accelerates until space itself curves around the mass. As the core contracts, the curvature intensifies. Eventually it reaches a point where the curvature becomes so extreme that escape becomes impossible. That point is the event horizon. You don't need to imagine it as a solid surface. Instead, consider it a location where the structure of space-time changes character. Light normally travels in straight lines through space. Near a black hole, those straight lines become curved. The closer light gets to the horizon, the harder it becomes for it to climb outward. Right at the boundary, the curve becomes complete. Beyond it, all paths lead inward. This entire process raises an interesting point. When we talk about the birth of a black hole, we are largely describing gravitational behavior. There is no new material forming. The matter simply becomes arranged in a configuration that changes how space-time behaves. The event horizon is not a barrier made of matter. It's a mathematical feature, defined by the geometry surrounding the singularity. If the singularity didn't form, the event horizon wouldn't exist. They're connected by the curvature that gravity imposes. Other types of black holes form through different paths. Some arise not from collapsing stars, but from the merging of smaller black holes. When two black holes spiral together and combine, the mass of the final one becomes greater, and the event horizon adjusts accordingly. The merger generates gravitational waves, ripples in space-time that travel outward at the speed of light. These waves have been detected by observatories like LIGO and Virgo, confirming predictions Einstein made decades ago. Still, even in these cases, the event horizon forms quietly. No matter how dramatic the merger might be inside the gravity well, no light escapes to reveal the details. There are also supermassive black holes, the enormous ones found at the centres of galaxies. Their origins are less straightforward. They didn't begin as ordinary stars collapsing. They may have started as smaller black holes that grew by gathering material over long periods, or from the collapse of early massive clouds of gas before stars existed. Their size can reach millions or billions of times the mass of our Sun. Yet the basic rule stays the same. Wherever enough mass gathers in a small enough region, the gravitational curvature can create an event horizon. Thinking about the birth of a black hole this way removes some of the intimidation often associated with them. They aren't mysterious because they disregard physics, but because they push physics to its limits. The formation process follows a sequence that fits neatly into our understanding of stellar evolution. It's the consequences of the collapse, the intense curvature, the loss of outward communication, the effects on time that make black holes stand out. But none of these features break the laws of the universe. They demonstrate them. To keep things steady, imagine how the star appeared before all this happened. A massive sphere of glowing plasma, radiating light into space. That light travelled across the vacuum, reaching nearby systems or drifting unnoticed into darkness. Inside the star, fusion maintained the balance. But as the star aged, the pattern shifted. Helium built up, the core grew denser, radiation pressure fluctuated. Over millions of years, the star approached instability. This slow movement through different stages is part of the natural cycle. The collapse itself, though fast, is not chaotic. It's the last predictable step. If the star were slightly less massive, it would become something else, perhaps a neutron star or a white dwarf. But stars above a certain mass threshold continue collapsing past those points. Scientists have worked out the details of this collapse using both theory and observations. Supernova remnants show where stars release their outer layers. Measurements of isolated regions with strong gravitational effects reveal where black holes now reside. The connection between the explosion and the core left behind completes the picture. Each step has evidence supporting it. Even though the singularity remains hidden, the effects around it leave a clear signature. Gravity tells the story. The formation doesn't produce distortions in space that the eye can catch. There is no flash marking the horizon's appearance. Instead, gravity quietly rearranges the region. Everything else becomes dim because the light cannot escape. Much of the surrounding material gets pulled in. Some forms an accretion disk, heating as it spirals inward. Some may be ejected along powerful jets, especially if the black hole spins. Such jets are visible from Earth across extreme distances and help astronomers locate black holes in galaxies far away. But the moment of birth remains concealed behind the collapsing layers, leaving only the new gravitational structure as evidence. This slow build-up toward understanding the formation of a black hole prepares us for where the journey leads. Once the black hole exists, its behavior becomes stable. It doesn't flicker or pulse on its own. Its gravitational pull remains constant. Over time, it might grow by absorbing nearby material or stay mostly unchanged. The process is guided almost entirely by mass and the way spacetime responds to it. This predictability is comforting in a way. Even though the environment near a black hole becomes extreme, the physical principles controlling it remain steady. As we continue exploring the nature of this cosmic structure, it helps to keep in mind how it started. The event horizon didn't appear out of nowhere. It formed naturally from the collapse of a star that had exhausted its fuel. Gravity shaped it. The star's life cycle prepared it. Nothing about its creation stands outside the rules of the universe. It's simply one of the possible outcomes when enough mass gathers in a small enough volume. Holding that perspective makes it easier to move forward. We've traced the path from a living star to the quiet emergence of a gravitational boundary. There is still much to explore, and each step brings us closer to seeing how the event horizon functions as both a boundary and a gateway into deeper questions. Moving deeper into the subject means slowing down enough to look at gravity in a way that isn't rushed. Most of us live with gravity constantly, but we rarely think about what it actually is or how it behaves. It holds us to the ground, keeps planets orbiting stars, and shapes the overall structure of the universe. But those facts alone don't reveal much about how gravity changes near something as extreme as a black hole. If we want to understand what happens close to the event horizon, we need to understand the environment gravity creates there, and that means building a clear picture of how gravity behaves from the ground up. Gravity began as a force described by Isaac Newton. He treated it as an attraction between masses, simple and direct. You have mass, the Earth has mass, and the attraction between the two is what keeps you anchored. This description works well for everyday life. It can predict how apples fall, how planets orbit, and how spacecraft navigate the solar system. For a long time, this was enough. But gravity near a black hole doesn't behave the way Newton's model predicts. The differences become noticeable only when gravity reaches extreme strengths, and that's why a broader explanation was needed. Albert Einstein introduced that new explanation with general relativity. In that framework, gravity isn't a force in the traditional sense. Instead, it's the way space and time bend in response to mass and energy. This bending creates paths that objects naturally follow. Whether it's a planet moving around a star or light travelling across the cosmos, everything follows the shape of space-time. This shift in perspective might sound complicated at first, but the concept becomes clearer when you imagine space not as an empty nothing, but as something that can curve, stretch, and shift. Rather than thinking of gravity as pulling things downward, Einstein's view suggests that objects move toward each other because the space between them has curved. A simple example is to picture a heavy ball placed on a flexible sheet. The sheet dips under the weight. If you roll a smaller ball nearby, it follows the curved slope created by the heavier one. It's not being pulled in directly, it's just following the contours of the sheet. This analogy works as a starting point, although real space-time is more complex, involving 3 spatial dimensions and time all woven together. As we keep easing into this idea, the sheet analogy helps us understand why black holes create such strong gravitational environments. When a massive star collapses, its mass becomes concentrated into a very small region. The curvature of space-time deepens dramatically. In the sheet analogy, it's like adding more and more weight until the dip becomes extremely steep. Light follows the curves of this dip as well. Near a black hole, light tries to follow the straightest possible path, but those paths are all directed inward because the space-time curvature is so intense. This is the foundation for understanding the event horizon. It's not a wall, a barrier, or a surface made of matter. It's simply the place where the curvature becomes so steep that nothing travelling forward in time can escape outward. Every path an object can take leads inward. Nothing about this requires mystical behaviour. The rules of space-time tell objects where to go, and near an event horizon, the available routes point deeper and deeper into the gravity well. The geometry becomes even more interesting when you consider how time is included in this picture. Time is not separate from space in Einstein's theory. They form a single structure known as space-time. Mass doesn't just bend space, it also affects the flow of time. The stronger the gravitational field, the slower time moves relative to locations with weaker gravity. This isn't something we feel physically. If you were standing closer to a massive object, your personal experience of time would feel normal. Seconds would still pass at their usual pace for you. But someone observing you from farther away would see your time move more slowly. On Earth, these differences are tiny but measurable. Atomic clocks placed at different altitudes show slight variations because the gravitational field changes with height. A clock at sea level ticks more slowly than a clock on a mountain. The difference is incredibly small, but it becomes meaningful for precise measurements. Extend that idea to a black hole, and the effect becomes massive. Time near a black hole moves at a noticeably slower rate than it does far away. This slowing of time is essential to understanding what happens as we approach the event horizon. It shapes our expectations about motion, light, energy, and how different observers see the same event. The space-time around a black hole is so strongly curved that the flow of time near the horizon becomes extremely slow compared to the outside universe. Someone falling inward experiences their journey normally, but to a distant observer, the infalling person appears to slow down, dim, and fade from view. All of these effects stem from the same underlying structure: gravity bending the fabric of spacetime. The fabric analogy isn't perfect because real spacetime isn't a surface, but the idea of curvature still helps. This curvature guides everything that happens near a black hole. It changes how distances behave, how time flows, how objects accelerate, and how light moves. When we talk about the void around a black hole, we aren't talking about an empty hole punched into the universe. We're talking about a region where the structure of space-time itself is shaped in a very specific way. Different black holes shape this fabric differently. A non-spinning black hole creates a symmetrical curvature around itself. The space looks the same in every direction. A spinning black hole, however, twists the fabric as well as bending it. Rotation drags space-time around the black hole, an effect called frame dragging. In the sheet analogy, this is like twisting the surface while also pressing down on it. This combination changes the paths objects can follow. It creates regions where space-time itself is pulled around, making it harder to stay still relative to the stars around you. If you tried hovering near a spinning black hole, you would feel the need to rotate to keep up with the dragged space-time, even if you were using engines or theoretical supports. Frame dragging introduces features like the ergosphere, a region outside the event horizon where nothing can remain stationary relative to distant stars. Inside the ergosphere, space-time drags so strongly that even standing still requires moving along with the rotation. The closer you get, the stronger this effect becomes. Eventually, all paths inside the ergosphere point forward in the direction of the black hole's spin. This region doesn't trap light permanently like the event horizon does, but it creates conditions that wouldn't be possible around non-spinning black holes. All of this comes from the same principle. Mass changes the structure of space-time, and that structure determines the motion of everything within it. You don't have to imagine the black hole actively grabbing things. You only have to consider that space-time has been shaped into a form where all available paths lead inward. In the case of a spinning black hole, the inward paths also twist. As gravity grows stronger, other effects appear. The curvature of space-time can become so uneven that different parts of an object experience different gravitational strengths. This difference is sometimes described in terms of tidal forces. Near Earth, tidal forces are mild. They affect the oceans more than they affect people. But near a black hole, especially a small one, the differences can become intense. The parts of an object closer to the black hole experience more gravitational pull than the parts farther away. This difference can stretch objects. For extremely small black holes, this stretching becomes severe enough that it would tear objects apart long before they reach the event horizon. However, the experience changes dramatically depending on the black hole's mass. A supermassive black hole has a much gentler gradient near its horizon. Even though its total gravitational pull is enormous, the change in pull over short distances is much smaller. This is why falling into a very large black hole would feel very calm initially. The tidal forces would be weak at the horizon, giving no indication of the curvature you're crossing. The stretching would only become extreme deeper inside. This distinction helps us understand that black holes aren't uniformly harsh environments. Their size shapes the severity of the conditions near them. Thinking about gravity as a geometric effect instead of a force gives us the right foundation to understand the void surrounding a black hole. The void isn't empty in a way that confuses or contradicts physics. It's simply a region that has been shaped by the star's collapse. Even if the black hole later grows by absorbing additional material, the same principles remain. Space-time bends according to mass and energy, and objects move along the paths created by that bending. One of the most interesting features of gravity near a black hole is how it affects light. Light normally travels in straight paths, but when space-time curves, light curves with it. This leads to a phenomenon called gravitational lensing. When light passes near a massive object, its path bends. Around a black hole, This bending becomes strong enough to create rings or arcs if the conditions are right. The first image of a black hole ever captured by the Event Horizon Telescope shows the bright ring created by glowing material orbiting near the event horizon and the lensing effects that wrap the light around the hole. The dark centre is the shadow of the black hole, not the event horizon itself, but an enlarged region where the trajectories of light have been bent so dramatically that none reach the observer. This image is a visual confirmation of how gravity shapes the void. The light doesn't disappear because something swallowed it. It disappears because the curvature directs its path away from the telescope. The paths light takes depend on the geometry, and the geometry near a black hole funnels many of those paths inward rather than outward. The result is the appearance of a shadow. Continuing through this calm exploration, we can notice that the void isn't a void in the everyday sense. It contains curvature, structure, and mathematical consistency. It's a zone where gravity's influence becomes extreme enough to reveal its deeper nature. When you're far from a massive object, space-time looks flat. The further you are, the weaker the bending. But as you approach something like a black hole, the curvature becomes more noticeable. The closer you get, the more dramatic the effects become, not because the black hole changes suddenly, but because you have entered a region where the curvature is stronger than anything encountered elsewhere in the universe. This region shapes time, space, motion, light, and information. Everything that happens near it reflects the underlying rules of general relativity, and even though some details remain theoretical, the core principles are supported by observations. Gravitational waves confirm how massive objects behave when merging. The shadow image confirms the predictions of strong lensing. Orbital measurements confirm the behavior of stars near the supermassive black hole at the center of our galaxy. All of these observations reinforce the idea that the curvature of space-time is the key to understanding black holes. Reaching the boundary of a black hole is not like arriving at a destination marked on a map. There is no signpost, no visible marker, no moment where anything displays a sudden change in colour, texture, or temperature. The event horizon is known as a threshold, but not in the ordinary sense. It doesn't behave like a door or a physical surface. Instead, it exists as a location defined entirely by the structure of space-time. To understand it clearly, the first helpful step is to focus on what it means for something to be unable to escape, even when moving at the fastest speed possible in the universe. The idea that light itself cannot escape from beyond the event horizon is central to everything that follows. Light represents the maximum speed limit allowed by the laws of physics. Nothing travels faster. That means if a boundary exists where even light cannot climb outward, nothing else can either. This boundary is the event horizon. It's not built from matter, nor is it formed from any type of substance. It is simply the place where the curvature of space-time becomes so steep that all directions lead inward. That fact is enough to give it significance, even without a physical structure. While the event horizon sounds like a dramatic edge, it isn't dangerous in the conventional sense. It won't announce itself or react to your presence. If you were drifting toward a sufficiently large black hole, you wouldn't detect any sudden shift as you crossed it. There would be no feeling of hitting something, no brightness dimming in an instant, no hint that you have passed a point that the rest of the universe can no longer communicate across. You would continue travelling inward without sensing anything unusual. The event horizon does not interact with matter directly. It simply outlines where escape becomes impossible. This calm and almost non-event nature sometimes surprises people, because the phrase "point of no return" suggests a dramatic turning point. It's natural to imagine something intimidating or abrupt happening as you reach the boundary. But most of the drama occurs from the perspective of someone watching from far away, not from the viewpoint of someone falling in. That difference in perspective is one of the most important parts of understanding what happens at the threshold. To explore that distinction, consider two observers, one drifting inward toward the event horizon and one watching from a safe distance. The person falling inward experiences time normally, with each moment following naturally from the one before it. They approach the horizon, pass through it, and continue inward. Nothing interrupts the continuity of their experience. But the distant observer sees a different sequence. As the infalling object gets closer to the horizon, its motion seems to slow down. Its signals become stretched out. Its light shifts toward longer wavelengths, dimming over time. Eventually the object appears to freeze in place right at the horizon. It never seems to cross it, at least from the external point of view. The light from the object becomes progressively fainter until it fades completely. This visual freeze is not the object actually stopping. It is the effect of gravitational time dilation. Time moves differently in strong gravitational fields. At the event horizon, time passes so slowly relative to the outside universe that signals sent upward take longer and longer to reach distant observers. Each signal gets stretched into a longer moment. The object isn't frozen at the horizon. The outside observer simply receives information more slowly, as time near the horizon slows dramatically from their vantage point. This difference in observed time explains why the horizon feels like a silent threshold. For the one passing through, nothing strange occurs. For the one watching from far away, the event looks like it never finishes. This disagreement between perspectives is one of the reasons black holes capture so much attention in physics. It's not an illusion or a trick. Both observations are correct depending on the frame of reference. General relativity tells us that time is not absolute. It depends on gravity and motion. Near the event horizon, the strong gravitational field stretches time for the infalling observer. That stretching creates the impression of slowing from the outside viewpoint. The event horizon marks the place where this difference becomes extreme. It is also the location where the escape velocity matches the speed of light. Escape velocity is the speed required to break away from a gravitational field. Near planets or stars, this value is high, but still reachable by rockets or hypothetical high-speed objects. Near a black hole, the required escape velocity increases steadily as one approaches the center. At the event horizon, it reaches exactly the speed of light. No object can exceed that speed, so escape becomes impossible. This perspective helps us understand something important. The event horizon is not a limit in a structural sense. It's a limit created by the geometry of space-time. The closer you get, the steeper the geometry becomes. At the horizon, there simply isn't a direction you can travel that allows you to climb outward while moving forward in time. Every path curves inward, even paths that seem outward by intuition. This makes the event horizon a simple consequence of the way space-time bends when a massive object collapses. Because this threshold is not physical, it also doesn't resist anything. Matter does not accumulate on the horizon or pile up there. It simply passes through. The horizon does not function like a membrane or a surface. It has no thickness, no friction, and no resistance. It's a location where a mathematical boundary is crossed. What you feel depends on the gradients in gravity, not on the horizon itself. For very large black holes, those gradients can be small at the horizon, making the crossing quiet and uneventful. Even though there is nothing physically present to detect, the horizon still has properties. For instance, its surface area depends on the black hole's mass, spin, and charge. If the black hole gains mass, the event horizon grows. If it loses mass, perhaps through Hawking radiation over long stretches of time, the event horizon shrinks. These changes occur smoothly. The horizon adjusts to the black hole's new parameters without introducing breaks or irregularities. One of the most interesting properties of the event horizon is its relationship to entropy. Entropy is usually discussed in the context of thermodynamics, describing how disorder or the number of possible configurations of a system increases. Black holes, surprisingly, have entropy proportional to the area of their event horizon. This idea, proposed by scientists studying the thermodynamic behavior of black holes, suggests that the horizon plays a crucial role in how information is stored or processed. The connection between the horizon and information has led to long-standing debates in physics, including the information paradox. According to classical black hole theory, anything crossing the horizon becomes unreachable to the outside universe. But according to quantum mechanics, information should never be lost. Reconciling these two ideas remains an active area of research. Some proposals suggest that information might be encoded on the horizon itself in subtle ways. Others consider whether information can be recovered through radiation emitted by the black hole. While the details continue to be debated, the horizon sits at the centre of this scientific puzzle. None of this involves drama for an object falling inward. The horizon doesn't behave like a storage medium in any physical sense. The object crosses it without noticing anything, even though theories might describe what happens using concepts like encoded information. For the falling observer, the horizon remains silent. The quiet nature of the threshold becomes easier to grasp when we focus on the fact that space-time curvature changes gradually as you move inward. Nothing special distinguishes the horizon locally. Only the global structure of space-time reveals its importance. For example, a photon emitted inward or sideways from just outside the horizon can climb outward if its direction allows. A photon emitted right at the horizon with an outward direction would hover, never escaping but never falling inward. A photon emitted inward cannot escape. These differences help define the horizon mathematically. This hovering effect applies only to an idealized photon aimed perfectly outward. For anything else, the curvature pulls it inward or lets it escape. This balance point helps define the horizon's location, but again, nothing about this is sensed physically. The threshold remains invisible to the traveller. The behaviour of infalling objects also depends on the size of the black hole. In smaller black holes, the gravitational gradients near the horizon become intense. An object approaching the horizon would feel rapid stretching, as the gravitational pull on one part of the object differs strongly from the pull on another part. This stretching effect is often called tidal stretching. In very small black holes, it would be felt long before reaching the horizon. In large black holes, the tidal forces at the horizon can be mild. The interior becomes more extreme later, deeper inside. This variation means the event horizon doesn't always represent a boundary of harsh physical conditions. For supermassive black holes, the horizon could be crossed without discomfort for a time. As long as the tidal forces remain manageable, motion would feel natural. You wouldn't sense the curvature directly. You would only feel the effects when the gravitational gradients became too large to ignore, which might occur well after crossing the horizon, depending on the black hole's size. This helps explain another important idea. The event horizon does not create the extreme conditions often associated with black holes. Those conditions occur deeper inside. The horizon simply marks where escape becomes impossible. After that point, the geometry of space-time ensures that all paths lead inward. Beyond the horizon, the curvature strengthens, and the interior becomes a region where the behaviour of space-time continues toward greater extremes. From the perspective of someone outside, the horizon acts as a practical limit. Once crossed, no signals return. The inside of the black hole becomes unreachable. This restriction shapes how we think about black holes in physics. It defines where information becomes hidden. It determines what we can observe and what remains unknown. But for the one falling inward, the horizon does not perform any blocking. It does not push back. It does not interact. It simply marks a location where the structure of space-time changes how motion behaves. As we move further in this exploration, keeping this calm understanding of the event horizon's nature will help make sense of the experiences that might follow. The silent threshold marks a transition, not a physical impact. It separates the region where light and signals can reach outward from the region where they cannot. It sets the stage for studying the interior and the deeper consequences of gravitational collapse. Falling toward a black hole is not like falling through air, and it's not like sinking underwater. Both of those situations involve friction, resistance, or a direct sensation of gravity pulling downward. The journey toward a black hole feels different because the environment isn't acting on you through particles or air pressure. Gravity is shaping space-time itself, and you are following the path that space-time offers you. Nothing pushes or tugs in the usual sense. There's no wind, no rumbling, no sound. Space does not announce what's happening, it simply guides you forward. To imagine the experience in a steady way, it helps to start from some distance. At first, the gravitational pull feels familiar. It behaves like what you might expect near a massive object. The acceleration increases gradually, not suddenly. If you were drifting in a spaceship or a protective cabin, you'd experience the motion as a smooth increase in speed toward the center. The closer you get, the more noticeable the acceleration becomes, but not in a jolting or abrupt way. The shift is continuous. You would be weightless inside your craft because objects in free fall do not feel their own fall. Everything around you would float just as it does in orbit. Free fall creates a sense of calm movement, even when the speeds involved are enormous. From your perspective, you are simply moving along a natural trajectory. Nothing in your immediate surroundings gives away how fast that movement becomes as you approach the black hole. Farther out, stars still appear normal. The black hole itself doesn't reveal its center. There is no swirling tunnel. Most of the sky looks like it normally does, except that the region ahead appears darker, and the stars behind you might appear distorted due to lensing if you get close enough. The distortions begin small, stretching and bending the positions of stars as the curvature of space-time alters the paths of light. But early in the fall, this effect is light. You can still recognize the general layout of the sky. As the fall continues, the speed increases. There's no sensation of speeding up because you're not sitting against a surface or resisting motion. The sense inside your cabin remains the same kind of weightlessness that astronauts experience. The difference lies not in how you feel moment to moment, but in how the outside universe behaves as time moves forward. Your clocks tick normally for you. Your heartbeat remains steady. Your speech would sound normal to you. All the effects of time dilation appear only when compared to the outside world's timeline. So from your own point of view, the fall feels natural and consistent. Eventually, the region ahead grows darker. The event horizon appears almost like a void, not because it radiates darkness, but because it doesn't emit light. The surrounding matter, if any exists, might form a glowing ring or disk, but that's not guaranteed. Many black holes have no visible disk at all, making them appear as empty patches in space. The lack of light is not a signal of danger. It's simply the absence of reflected radiation coming from the surface of the horizon, since there is no surface to reflect it. As gravity strengthens, one of the first detectable changes appears in how light behaves. If you look back toward the direction you came from, you would notice a brightening of the stars behind you. Their light becomes compressed into shorter wavelengths due to the Doppler effect of your increasing speed. You wouldn't necessarily see this as a sudden flash. Instead, it manifests gradually. The starlight appears concentrated into a circular region behind you. Meanwhile, the sky ahead becomes dimmer and less detailed. The region around the black hole expands visually. This doesn't mean the black hole itself grows. It means the curvature of space-time bends incoming light so strongly that the view forward becomes more distorted. If your cabin has windows on all sides, you might notice something else. The apparent location of surrounding stars begins to shift. Light that would normally reach you directly begins bending around the gravitational gradient. Some stars appear duplicated or stretched. Your view becomes a mixture of familiar constellations and warped replicas. These distortions represent the lensing effects predicted by general relativity. None of this harms you, but it signals how the fabric of space-time is curving more dramatically as you descend. Different clues appear depending on the size of the black hole. For a supermassive one, the gravitational gradient is gentle at the horizon. This means that your experience remains calm and unchanged as you approach the boundary. The stretching of space happens on large scales, not small ones. Your body is too small relative to the black hole's mass to feel any difference. Tidal forces, which cause stretching, become significant only much deeper inside. So, as you approach the horizon of a supermassive black hole, you remain safe from dramatic forces. Your cabin stays intact. Your body feels weightless. You don't experience any acceleration pressing you in a direction. If the black hole is smaller, the gradients become stronger earlier. In such a case, you would notice the sensation of being pulled more strongly at one end of your body than the other. This difference leads to stretching forces. If the black hole is too small, the stretching becomes severe outside the event horizon. But since our scenario aims for clarity and safety, imagining a supermassive black hole provides a smoother path to understand the interior. The moment you cross the event horizon, nothing signals a change. No sound, no colour shift, no vibration occurs at the boundary. You simply pass through a region where escape becomes impossible. Your cabin cannot send messages outward anymore, but you still receive light from outside for a while. Signals entering from outside can reach you, but signals leaving from inside cannot reach anyone beyond the horizon. This asymmetry is one of the defining aspects of the event horizon. It doesn't cut off your awareness immediately. It only restricts outward communication. While inside, the curvature continues to deepen. The geometry of space-time shapes the direction you're falling. Everything inside follows the same inward-directed paths. You can no longer hover or maintain a stable position. Even with propulsion, reversing course becomes impossible. The inward direction is built into the space-time structure. Your engines would push, but the geometry doesn't allow a path that leads outward. This is not because anything resists your push. It's because the direction that corresponds to outward no longer exists as a forward-in-time path. Only inward paths move forward in time once you're inside. This shift in geometry becomes easier to visualize if you think of space-time coordinates being rearranged. Outside the horizon, space behaves normally. Time moves forward, and space provides directions you can move. Inside, time and space trade roles in a sense. The inward direction becomes similar to the direction of time. You cannot choose not to move inward, just like you cannot choose not to move forward through time. It's an unavoidable progression. As you continue falling, you may notice the starlight behind you growing narrower. The outer universe occupies a smaller region of your visual field. The blackness ahead expands as the curvature tightens. Your visual horizon shifts, but your internal experience remains steady. Your own sense of time continues normally. Clocks tick as usual. Heartbeats maintain their rhythm. Conversations, if you had a crew with you, sound natural. Nothing in your immediate environment signals that space is being reshaped around you. However, the signals you might still receive from outside begin to distort. Light arriving from the universe beyond becomes stretched into longer wavelengths. Colours shift gradually toward red, then toward infrared, and eventually beyond visible wavelengths entirely. The outside universe dims not because it has disappeared, but because the curvature alters the frequency of the light reaching you. Each photon follows a curved path, losing more and more energy as it comes inward relative to your frame. Eventually, the signals become too stretched to detect. This slow dimming creates the sense that the outside world is receding, even though the only real change is your position within the geometry. Inside your craft, everything still feels stable at this stage, as long as the black hole is massive enough. Pressure remains even. Structural stress doesn't spike. The feeling of weightlessness persists, but the tidal forces begin to increase slowly. These forces are not immediate or sharp, unless the black hole is small. In a large black hole, the stretching effect becomes noticeable only gradually. Your body would begin experiencing the subtle sensation of being pulled more in one direction than another. The effect would start small, like an almost imperceptible difference in tension across your body. Over time, it would increase. Objects around you might drift in slightly stretched trajectories, depending on their orientation relative to the inward direction. The stretching arises because the gravitational field changes rapidly over small distances. The part of your craft closer to the centre experiences slightly stronger gravitational pull than the part farther away. This difference increases as you fall deeper. For a while, the cabin compensates. Modern or hypothetical future materials might resist the deformation to some extent, but deeper inside, the difference becomes too large to ignore. The closer end of the cabin accelerates faster than the farther end. The structure begins to strain. Even before that point, your internal senses might detect the difference subtly. You might feel gently elongated along one axis. It wouldn't feel painful at first. It would feel like your body is being guided into a stretched posture that requires no effort to maintain. Over time, the force grows stronger. Muscles and bones can withstand small differences, but as the gradient increases, the stress becomes significant. The same applies to the cabin and its instruments. Their ability to resist deformation has limits. All of this unfolds while the environment remains silent. No sound travels in space. No physical contact occurs with any barrier or structure. Even as the forces increase, the change feels gradual. Nothing jumps to extremes instantly. The curvature deepens in a continuous way. The geometry dictates where you go and how you move, but it doesn't announce the changes with sudden jolts. At this stage, communication with the outside universe is long gone. You cannot send signals out. The physics of space-time prevents them from escaping. You may still receive some last fragments of stretched radiation, but eventually even those fade. The universe beyond the horizon becomes effectively unreachable. Inside, your path continues inward. Nothing reverses the direction. It is not possible to maintain distance from the center. The structure of space-time keeps narrowing the allowable pathways until only one main path remains, guiding all objects toward the center. The curvature increases faster as you approach the singularity. This tightening of the geometry intensifies the stretching effect. For a very small black hole, the stretching would have become extreme even before reaching the horizon. But for a supermassive one, the gentle beginning becomes more intense deeper inside. Eventually, the tidal forces grow beyond the limits of what any material can withstand. The craft would deform, instruments would break. Even then, the process would feel like an increasing pull rather than a sudden impact. At this depth, the environment is no longer something you can interpret with normal experiences. The curvature dominates every direction. Space compresses in some directions and stretches in others. Movement becomes dictated entirely by geometry. You're following a path that space-time has shaped for everything inside the horizon. Understanding this part of the journey helps prepare us for what lies even deeper. The experience transitions from a smooth free fall into the region where the structure of space-time controls the direction and intensity of motion more completely. Each step inward shows how gravity shapes not only paths and trajectories, but also the limits of what can exist without breaking apart. When we talk about stretching near a black hole, the word spaghettification often comes up, and despite the humorous tone of the name, the concept behind it is based entirely on physics doing what physics always does. The term refers to the process where an object becomes elongated due to differences in gravitational pull across its length. It sounds dramatic because the name conjures a vivid image, but the reality is that it's grounded in predictable behaviour. Gravity near a black hole becomes uneven over small distances. That uneven pull creates the stretching. Nothing about it is chaotic. It is simply the result of gradients that grow stronger as you move closer to the centre. To understand why the stretching occurs, it's helpful to think step by step about how gravity changes across your body. Far from a black hole, the difference in gravitational strength between your head and your feet is too small to notice. Gravity decreases with distance, but over the length of your body the difference is tiny. Even near planets or stars, that difference remains too small to produce a noticeable effect. But near a black hole, especially one with a small mass, the change becomes dramatic. The closer end of your body feels a much stronger pull than the farther end. That difference pulls you into a stretched shape along the direction of the fall. The stretching doesn't begin suddenly. It increases gradually as you fall. In a supermassive black hole, the initial part of the fall feels almost peaceful. The tidal forces start out small because the horizon of a massive black hole is large. The gradients in gravitational pull remain gentle for a while, which means there is no immediate discomfort. Your body doesn't begin elongating right away. Your craft remains intact at first. The sense of weightlessness continues. The curvature of space-time guides your fall, but you don't yet notice local distortions in how gravity pulls on different parts of you. Eventually, though, the gravitational differences grow strong enough to feel. The stretching begins as a subtle sensation. If your craft has windows, you might see objects drifting in ways that don't match what you're used to. One end of a floating object might appear to drift slightly faster than the other. If you drop a small tool, it may move in a way that reveals the difference in gravitational pull across its length. These early signals of spaghettification are gentle. You wouldn't mistake them for anything violent. They simply indicate that the curvature is becoming more pronounced as you fall deeper inside. It's helpful to think about why the stretching happens in terms of geometry. When space-time curves sharply, the paths available for objects become different depending on their positions. The inward part of your body is closer to the centre of the gravitational well. That part of you is pulled along a slightly steeper path than the part farther from the centre. Over time, the difference becomes more noticeable. Gravity isn't trying to tear you apart, it's following the shape of space-time. Your body is experiencing that shape physically. The result is a stretching along the direction of the fall. The name Spaghettification is informal, but it captures the direction of the effect accurately. You're pulled into a long, thin shape. Your width decreases because gravity squeezes inward from all sides. This squeezing occurs because gravity pulls not only downward, but also inward from every direction. It narrows your shape while lengthening it. That combination creates the stretched geometry associated with the term. If the black hole is small, the stretching becomes intense before reaching the event horizon. The closer you get, the more dramatic the difference becomes. A stellar mass black hole has a horizon only a few kilometers across. The gravitational gradient across even a single meter near such a black hole is enormous. An object falling in would be torn apart long before reaching the boundary. The stretching becomes extreme early in the fall. For a supermassive black hole, though, the horizon is large. It may be millions of kilometers across. The gradient near the horizon is mild. You could cross the boundary without experiencing significant stretching at first. Only as you progress inward do the tidal forces grow strong enough to overcome the strength of materials and biological tissue. The process still happens, but it's delayed. It unfolds deeper inside where the curvature tightens sharply as you approach the singularity. This distinction is important. Many people imagine that crossing the event horizon comes with an immediate pulling apart. That's not the case for large black holes. The stretching is a gradual process that depends on how sharply the gravitational field changes with distance. The intensity of the effect depends on the black hole's mass. A larger mass spreads the gravitational influence across a wider region, making the change less steep near the horizon. A smaller mass concentrates the same pull into a much smaller volume, making the gradient stronger. Inside a supermassive black hole, your experience continues to follow this pattern. As you move further inward, the stretching increases in a steady way. The cabin around you begins to deform. It may lengthen along the direction of the fall. The walls may experience stress that they cannot counteract indefinitely. At first, the deformation might be small, perhaps creating subtle creaks or structural shifts. Later, the forces become stronger. The curvature of space-time dictates that the difference in gravitational pull grows rapidly. No material can resist indefinitely. Your body begins to follow the same pattern. The stretching acts on you directly, elongating you in the direction of the fall. It compresses you from the sides. This sounds intense, but the onset is gradual. The stretching builds slowly enough that early stages would feel like being gently elongated. Only when the tidal forces become stronger than your body can withstand does the sensation become overwhelming. It's important to understand that spaghettification is not caused by the event horizon or by crossing it. The horizon is simply a boundary where escape becomes impossible. The stretching is caused by tidal forces, and those forces depend on gradients. They depend on how rapidly gravity changes over small distances. That's why small black holes cause the effect early. Large black holes cause the effect later. The horizon's presence does not create the stretching. The interior curvature does. As you fall deeper, the geometry becomes more extreme. Space contracts more tightly inward. Everything is pulled toward the center. The stretching grows stronger because the difference in gravitational pull increases. The cavities in your craft begin to distort more rapidly. Loose objects drift in elongated paths. The structure bends. Instruments break. Signals inside the craft may fail as their components are stressed beyond their design. Your visual field also changes. The outer universe shrinks into a narrowing region behind you. The light reaching you is stretched into longer wavelengths. Colours fade. Eventually all visible light from outside shifts beyond the visible spectrum. You no longer see the stars or any hint of the universe beyond the horizon. The interior becomes dominated by the geometry of space-time itself. There's no external reference to compare your motion against. Only the inward direction persists because space-time offers no alternative path. The tidal forces continue increasing. The stretching becomes more noticeable. If you imagine the shape of your body at this point, the length grows steadily. The compression from the sides increases. Muscle tissue, bone structure, and internal organs all experience the pull. The shape becomes elongated because every point in your body is following its own geodesic. A geodesic is the natural path that space-time offers. Points at different positions follow paths that diverge. That divergence creates the stretching. The physics behind this remains steady and predictable. Nothing about the interior becomes random or chaotic. It is simply a region where the rules governing space-time become extreme. Every object falls inward. Every object stretches. Every material experiences stresses that become too large for any structure to resist. The stretching continues. For a moment, it's worth considering what might happen if the black hole were rotating. Rotation alters the geometry. It drags space-time around with it. This dragging affects the shape of the tidal forces. It alters the trajectories of objects. It can make the stretching occur in slightly different orientations, but the overall effect remains similar. Tidal forces still dominate. The stretching still occurs. If the black hole has an accretion disk, the environment outside the horizon may look more active. But once inside, the disk no longer matters. The fall becomes governed by the geometry alone. No matter what the initial conditions were, the interior structure leads everything toward the center. Some theories suggest that the singularity might not be a single point. It could be a ring in the case of a rotating black hole. It could be something different in theories that include quantum effects. But regardless of the exact structure, the tidal forces increase dramatically as you approach the central region. The stretching becomes complete. No physical object remains intact. The geometry forces everything into narrower shapes until the limits of material strength are exceeded. In this calm explanation, the term polite horror makes sense in a particular way. The process doesn't occur through violence or chaos. It unfolds slowly, step by step, following rules that never deviate. The stretching becomes severe, but it follows a clear pattern. It's not sudden or unpredictable. It is consistent with the geometry of space-time. The most difficult part isn't the abruptness, it's the inevitability. Once inside the horizon, the inward path is built into space-time. There is no path outward. Even in these extreme conditions, the concepts remain structured. Gravity behaves according to mass and distance. Tidal forces arise from gradients. The stretching increases with curvature. These principles hold regardless of the size or rotation of the black hole. The details might change slightly, but the overall pattern persists. As we move closer to the environment defined by the event horizon, it becomes easier to focus on how light behaves there. because light reveals the structure of space-time in a way nothing else can. Light always travels at the same speed, but the path it takes depends entirely on the geometry it moves through. Near a massive object, the path bends. Near a black hole, the bending becomes extreme. The direction of travel changes, not because the light chooses to turn, but because space-time curves so sharply that all straight lines become distorted. The region around a black hole includes an area where light can still escape, another where it can escape only if it's pointed outward with perfect precision, and a final region where escape becomes impossible no matter which direction the light tries to go. These boundaries are defined not by walls, but by the paths available inside space-time. Light follows those paths naturally. It cannot slow down, speed up, or take shortcuts. It travels along whatever space-time curvature allows. To understand this more clearly, imagine a photon emitted by a small lamp in your cabin as you fall toward the horizon. The photon shoots outward, moving at light speed. Farther from the black hole, that photon has a straightforward path. It travels outward, leaving the region safely. But as the curvature increases, the path bends more sharply. If the photon is emitted too close to the horizon, the bending becomes important. Even if it's emitted outward, its path may arc back inward. Only photons that leave at certain angles escape. The closer you get to the horizon, the narrower the allowed angles become. At the horizon itself, only a photon aimed perfectly outward, following a specific trajectory, would hover in place relative to the horizon. Any deviation, however small, sends it inward. This hovering behaviour is one of the clearest signs of how space-time behaves at the boundary. A photon emitted outward from exactly the right position, at exactly the horizon, stays suspended, never escaping, never falling in. It isn't held there by a force, it's simply following the path that space-time offers, a path that neither leads out nor leads in. That path exists only at the horizon itself. Any photon emitted from slightly inside or with a slightly different direction will move inward. Any photon from slightly outside with the right direction can still escape. Because of this behaviour, the event horizon acts like a limit for light. Nothing pushes against the photons. There is no barrier that slows them. Instead, the geometry has removed all outward paths that lead away from the centre while still moving forward through time. Inside the horizon, an outward direction simply doesn't exist in the same sense. Time itself has been bent inward. Before reaching this extreme, the region around the horizon still allows light to escape, but in narrower and narrower paths. As you fall, if you turn on a flashlight and shine it toward what you think is outward, the beam doesn't behave the way it would in open space. Instead of spreading outward in a broad cone, the beam narrows and bends. Some of the photons escape, but many curve back inward. From inside the cabin, watching the beam distort gives you a clear sign that you're entering a place where the geometry is no longer gentle. Even so, the bending of light is not accompanied by noise or pressure. All of the effects come from curvature. The photons still move at the same speed, but the direction of travel changes. If you shine the same flashlight backward, toward the stars behind you, the photons have an easier time escaping because they are moving in a direction that works with the curvature. Even then, the paths are distorted. The light spreads unevenly. The beam might appear to split or arc slightly, depending on the exact position and the rate at which space-time is curving around you. Your view of the outside universe now shows increasing distortion. The closer you get, the more the stars behind you appear to gather into a shrinking circle. The region ahead, where the black hole lies, widens into an expanding dark sphere. This isn't because the black hole is growing, it is because the bending of light near the horizon makes the dark region appear larger. Photons that might have reached your eyes from directions near the black hole are instead being bent away or prevented from reaching you. The result is an expanding circle of darkness whose boundary marks the extent of light paths you can still receive. As the horizon nears, this circle tightens further. Light arriving from outside becomes redshifted, meaning its wavelength stretches. Colours shift toward red, then toward infrared, then beyond visibility. Eventually, the visible light from the universe outside fades entirely, leaving only the dimmest traces of longer wavelengths reaching you. This fading doesn't happen suddenly. It's slow and gradual. The dimming reflects the increasing difficulty photons have in climbing inward through the curvature. Their energy decreases relative to you because of the gravitational differences between where the photons originated and where you are now. In other words, the light still exists, but the wavelengths become too long for your eyes to detect. Instruments might detect some signal if they were sensitive to long wavelengths, but even those signals weaken until they reach a threshold beyond which no detectable radiation arrives. This is one of the ways the horizon isolates the interior. Light loses energy as it climbs the curvature, and eventually it cannot reach you at all. If you were to stand still outside the horizon and shine a laser toward the black hole, the beam would bend and stretch. The portion that strikes near the horizon might curve into it. Portions that start farther away might bend but still escape. The distribution of possible paths narrows as the horizon becomes closer. This is why the boundary appears like a dark sphere when viewed from outside. Light cannot reflect off anything, and light behind the horizon cannot escape. Nothing within it emits photons that reach your viewpoint. The blackness is absolute. Inside the fallen cabin, however, the view continues to change. As the outside light fades, you may notice that any illumination you create inside behaves differently depending on the direction. A photon emitted forward, toward the black hole, moves inward quickly. A photon emitted sideways may curve inward or outward depending on the precise orientation. A photon emitted backward still has the greatest chance of escaping inward curvature, but even those paths become more limited as you approach the horizon. The term last stand refers to the final range of angles where photons can still escape. As you near the boundary, the cone of escaping directions narrows. At first, half of all directions allow photons to escape, then it becomes a smaller range. Eventually, only a thin slice of directions remain. Finally, only a perfect line pointing directly outward remains at the boundary. Any slight deviation takes the photon inward. The narrowing is steady and predictable, not sudden. It reflects the increasing steepness of spacetime near the horizon. This narrowing of escape paths also shapes how the black hole appears from outside. If you were watching someone fall in, you would see them fade gradually as the light they emit becomes redshifted. Their final photons stretch into longer wavelengths. Their signals take longer to reach you. Their clock appears to slow. Eventually, their image dims and disappears. This fading reflects the fact that the last photons arriving from them were emitted just before crossing the horizon. The photons emitted after crossing never reach you. The extremely redshifted final photons become too stretched to detect. From inside, though, the experience is different. You do not see your own light fade relative to yourself. Your instruments behave normally. The changes occur only in how much light you can receive from the outside universe. You gradually lose contact with the external world. Light becomes distorted, stretched, delayed, and eventually disappears. This doesn't feel sudden because the change is tied to the curvature, rather than to a direct intervention. All the light signals fade because the geometry restricts their ability to reach you. The behavior of light also reveals something important about energy. When a photon moves upward through a gravitational field, it loses energy. This doesn't mean it slows down. Photons always travel at the same speed. Instead, the energy loss appears as a change in wavelength. The photon stretches into a redder colour. This stretching continues until the wavelength becomes arbitrarily long. Photons coming inward toward you stretch more and more as you fall inward. The loss of energy reflects the difference between the gravitational potential where the photon started and where you are now. The closer you get to the horizon, the stronger the redshift becomes. This redshift is one of the main indicators of the boundary, but it is not something you feel physically. You don't sense the stretching of light directly. You only notice it visually. As the signals stretch, the colours change, then fade. Eventually, no photons from outside the horizon reach you. Your world becomes defined solely by the interior. The boundary's function is complete at that point. You have permanently lost access to the outside universe. Even though no light escapes from inside the horizon itself can radiate in a specific quantum sense, according to Stephen Hawking's proposal. Hawking radiation arises from quantum effects near the horizon. It's not light escaping from inside. It's a consequence of particle-antiparticle interactions at the boundary. To an observer far away, this radiation makes the black hole appear to emit energy slowly. But none of this helps anyone inside the horizon. The radiation comes from just outside the boundary and does not carry information from within. This process of Hawking radiation is slow for large black holes. A supermassive black hole radiates so little that the effect becomes noticeable only over timescales longer than the age of the universe. Still, the existence of this radiation ties into the larger question of information. Some theories propose that information about what enters the black hole might be encoded in subtle changes in this radiation. Others suggest the information is stored on the horizon itself. These ideas are part of ongoing discussions in theoretical physics. But for someone falling inside, none of these discussions affects the actual experience. Light simply stops arriving from outside, and any information about the exterior becomes unreachable. The behaviour of light also helps define the shape of the shadow observed by telescopes. The shadow is not the event horizon itself. It is the region where photons orbit the black hole in unstable paths. These photon orbits exist outside the horizon. If light passes at precisely the right angle and altitude, it can circle the black hole before escaping. This creates a glowing ring of light around the shadow. The centre appears dark because photons that would have filled that region have been redirected inward. The photon sphere, not the horizon itself, determines the appearance of the shadow. Inside that region, photons inevitably fall inward. The shadow shows where spacetime geometry dominates the behaviour of light. Following the light paths helps illustrate how space becomes structured as you approach the horizon. The curvature guides everything in predictable ways. The region where photons can orbit marks a significant change in how they behave. Closer in, the escape paths narrow. Right at the horizon, the last possible path exists but only for photons aligned perfectly outward. Inside, no paths escape. This structured progression describes the way geometry changes near the boundary. Continuing through the fall, the narrowing of light paths parallels the narrowing of your connection to the rest of the universe. The view behind you shrinks, the colours fade, the distortion increases, your surroundings lose external reference points. All of this reflects the increasing dominance of space-time curvature over the behaviour of light. The photons that enter from outside follow paths that lead inward, and the photons that might have escaped are trapped. The inside becomes a region where the absence of external light provides clarity about what direction the journey leads. Every path moves inward. Every photon emitted from you goes inward, unless it is aligned perfectly outward at the boundary, which only occurs exactly at the horizon. As soon as you cross, even that narrow path no longer exists. Every photon you emit after crossing remains inside. Understanding how time behaves near a black hole requires setting aside everyday assumptions, because time feels reliable to us in normal situations. Seconds pass one after another, clocks tick steadily, and the rhythm of your thoughts remains consistent. Gravity on Earth affects time, but the difference is so small that you never sense it directly. A clock placed at the bottom floor of a building ticks slightly slower than one placed at the top, but the difference is far too tiny for a person to feel. Even highly precise instruments require careful setup to measure it. Near a black hole, however, the situation becomes extreme enough that the effect becomes meaningful even on human scales, especially when comparing 2 points of view. The most important idea to hold on to is this: time does not pass at the same rate everywhere. Gravity influences the passage of time. Motion influences it as well. These influences are predicted by relativity and confirmed through experiments. but they become overwhelmingly strong near the event horizon, where the curvature of spacetime reaches its most intense form. As you fall toward the horizon, time from your own point of view feels exactly the way it always does. You do not sense anything unusual about the passage of seconds. Your breathing remains steady, your heartbeat remains steady. If you are counting silently, nothing interrupts the rhythm. Your personal clock keeps time normally. This continuity is one of the key features of the experience. Nothing inside your mind or body warns you that time is behaving differently relative to the outside universe. The difference appears only when comparing two observers. One stays far away, the other falls inward. Their clocks do not agree. If the distant observer could watch your clock, the tick would appear to slow down. Each second would take longer to arrive. The slowing becomes more pronounced as you approach the horizon. Eventually, from the outside perspective, your seconds stretch toward infinity. Your fall appears to freeze in place. You do not freeze from your own perspective, but the outside observer sees your movement slow, then slow again, then slow further, until your final moments before crossing seem to take forever. This difference can be described simply. Time moves at different speeds in different gravitational fields. The stronger the field, the slower the passage. The black hole creates an extremely strong gravitational field. The curvature near the horizon slows time drastically. The deeper you fall, the slower time moves relative to the outside universe. The mathematics of general relativity describes this precisely, but the feeling remains ordinary as long as you experience it yourself. Imagine holding a small digital stopwatch. You start it as you fall. From your viewpoint, the seconds advance smoothly. 10 seconds feel like 10 seconds. 30 seconds feel like 30 seconds. You never lose that sense of continuity. Meanwhile, the outside observer sees your stopwatch ticking more slowly. The 10th second might appear late. The 30th second might appear extremely late. Eventually, the stopwatch seems almost stopped. The delay grows without limit as the horizon nears, and yet you continue falling normally. This mismatch leads to one of the most surprising consequences. From the outside perspective, you never cross the horizon. Your image fades but lingers near the boundary. Light signals from you become more stretched, more red-shifted, and slower until they vanish. The outside world never sees you cross. But from your own perspective, the crossing occurs in finite time. You fall in. Nothing halts you, nothing delays you. There is no indication of the outside world's infinite delay. The two perspectives coexist. Both are correct according to relativity. There is no single correct timeline. There are two reference frames, each with its own description of events. The important part is that the disagreement does not produce contradictions. It arises naturally from the structure of space-time. To explore this further, consider the exchange of signals. If you send a message outward as you fall, the signal takes longer and longer to reach someone far away. If you try to send one at the horizon, it never escapes. The delay becomes infinite from the outside perspective, but from your perspective, the signal leaves you normally. The curvature prevents it from escaping. This means that once you cross, you cannot communicate outward under any circumstances. The arrow of communication becomes one way. Signals from the outside can still reach you for a while, but signals from inside cannot reach out. If someone outside tries sending you a message as you fall, the message can reach you even when you are very close to the horizon. It becomes stretched, dimmed, and delayed, but it arrives. However, once you cross, even inbound messages suffer the same fate as outbound ones. The geometry of space-time eventually prevents both directions. The outside universe continues to exist, but you no longer receive anything from it. From your perspective, the outside fades not because it disappears, but because light cannot reach you. This asymmetry becomes clearer when imagining two clocks, one with you, one far away. They both tick steadily. But the clock inside seems slow to the outside observer, and the clock outside seems fast to the falling observer once they're deep enough. The deeper you go, the greater the difference grows. This time, difference also shapes the apparent duration of your fall. From your viewpoint, the fall to the horizon takes a finite amount of time. From the outside viewpoint, the fall takes forever. You fall slower and slower until you appear to stop. Your image fades rather than completing the fall. At no point does the outside observer see you accelerate sharply or vanish suddenly. The fade is gradual and follows predictable rules. The light from you becomes too stretched to detect. Eventually, your final signal becomes so redshifted that it moves beyond the range of detectors. Your image fades away in a continuous, smooth arc of time. At the same time, you continue falling. Nothing slows you. You cross the boundary in what feels like normal seconds. This moment is unremarkable from your perspective. There is no sudden shift, no jolt, no indication that the event horizon has been reached. Only when you look outward do you see changes. The universe behind you shrinks and stretches. The light reaching you becomes more distorted. The piece of the universe that remains visible continues to shrink into a smaller region. The slowing of time becomes even more dramatic when comparing someone who stays outside for a very long duration. If someone far away waits while you fall, they might witness events occurring around them in normal time. They age normally. Clocks around them tick normally. They might watch stars move, planets orbit, and other cosmic events unfold. Meanwhile, your fall appears stuck near the horizon. The more time passes outside, the more dramatic the time difference becomes. Some descriptions imagine a scenario where someone waits millions of years watching you fall. Your signals would continue slowing. Your image would continue stretching. You would remain fixed near the horizon from their perspective, long after civilizations rise and fall. But for you, the fall would have already continued inside. This extreme mismatch in time becomes more noticeable as gravity increases. Near Earth, the effect is too small to feel. Near neutron stars, the effect becomes measurable but not overwhelming. Near black holes, especially at the horizon, the effect becomes enormous. Time effectively stretches toward infinity from one direction. It is important to emphasize that nothing about the slowing is caused by personal experience. You don't feel time stretching. You don't sense clocks slowing. You don't notice your heartbeat changing speed. You continue experiencing the same flow of time you always have. All the stretching occurs when comparing your frame of reference with someone else's. To make the difference more concrete, imagine two identical clocks. One remains far away, one falls with you. The clocks are perfectly synchronized at the start. As you fall, your clock remains synchronized with you. You watch it tick. You have no complaints about its operation. The outside observer watches their own clock tick normally. But when they receive signals from your clock, each tick appears slower than the last. 1 second intervals become longer intervals. This difference grows until the signal becomes too stretched to detect. If you could see their clock while falling, you would notice the opposite effect. Their clock appears to tick faster. Its seconds appear shorter. Their timeline accelerates compared to yours. But inside the horizon, you can no longer receive their signals, so the comparison breaks down entirely once communication becomes impossible. This behavior is connected to gravitational redshift. As light climbs out of a gravitational well, it loses energy. Wavelength increases. The signal becomes redder. Eventually the redshift becomes infinite at the horizon. Signals from inside cannot escape. This redshift is directly linked to time dilation. When a signal from your clock becomes redshifted, that redshift corresponds to each tick appearing slower. The slower ticks represent slower time relative to the outside frames. Time dilation also influences the appearance of physical processes. If you dropped an object into the black hole and watched it from far away, the object would slow, dim, and stretch in appearance. If you dropped two objects, one slightly earlier than the other, the distance between them would appear to shrink as they approach the horizon. Their movement would be governed by the same time dilation effects. From your own viewpoint, the separation remains normal. Both objects fall smoothly. The only difference is the order in which you encounter different regions of curvature. Nothing seems out of place. The slowing of time has deeper implications in physics. The idea that time slows near massive objects helps explain how gravity works in general relativity. Gravity is not a force, but the effect of spacetime bending. When spacetime bends, time bends as well. The rate of time changes depending on your location. This affects everything from the motion of the light to the orbits of planets. The slowing of time is not an optional detail, it is central to how gravity works. Near the horizon, time slows by such an extreme amount that everyday intuition loses its usefulness. The difference between the fall and the outside world becomes enormous. In some descriptions, if you fell into a supermassive black hole and someone waited far away for an extremely long period, you could theoretically witness large-scale events in the universe unfold from your viewpoint. Galaxies might move, stars might evolve, the outside universe might age faster relative to you. But in practice, the fading of signals prevents you from receiving much information. The curvature stretches the light so far that it becomes undetectable before such differences matter. The slow fall also connects to something called the horizon problem. From the outside viewpoint, the fall appears infinitely slow, but from the inside viewpoint, the fall continues normally. This discrepancy represents one of the cleanest examples of relativity's impact on time. The two viewpoints cannot be reconciled into a single timeline. They coexist. Each is correct within its own frame. Nothing about the slowing signals danger. You don't lose consciousness. Your thoughts continue. The steady pull inward continues. The environment around you changes shape due to curvature, but your internal sense of time remains steady. The gradual loss of signals from outside feels like a dimming rather than a shock. The narrowing of visible light feels like a retreat rather than a collapse. The transition is gentle in terms of sensation, even if the physics behind it becomes extreme. As your fall continues deeper, time dilation continues to increase. But this increase no longer matters to you because communication with the outside world is lost. The rest of your journey becomes defined solely by the interior geometry. The difference between your timeline and the outside timeline still exists, but there is no longer a way to compare them. Once the horizon is crossed, your experience detaches from the external universe entirely. Time remains personal. The deeper regions shape what happens next. From the moment someone begins falling toward a black hole, the experience divides into two completely different stories. One story is the experience of the person who is falling. The other is the experience of the person who is watching from a safe distance. Both stories follow the laws of physics, but the two versions diverge so strongly that it becomes difficult to align them in ordinary language. The perspective from outside is shaped by relativity, especially by the way time and light behave near strong gravitational fields. Nothing about the view from far away is imaginary. It reflects what relativity predicts and what observations of extreme gravitational environments confirm. Imagine you are the outside observer. You are far from the black hole, far enough that the gravitational field around you feels weak and normal. You hold a telescope or a set of instruments capable of tracking the person falling in. The first part of the journey looks familiar. The person drifts closer. Their motion accelerates slightly, then more noticeably. Light from their cabin or suit reaches you easily. Communication signals reach you without delay you would notice. Everything looks normal. As time moves on, the gravitational field they are entering becomes more relevant to what you see. You notice their motion changing, not because of anything they do, but because the curvature of space-time around them begins altering how their movement appears from your position. Their fall seems smooth at first. You expect them to continue accelerating inward. But the closer they get to the event horizon, the more their motion appears to slow down. This slowing is not caused by friction, collision or resistance. It's caused by the time dilation you already know affects anything near the horizon. Their personal time continues passing normally, but the signals reaching you reflect the passage of their time, and those signals take longer and longer to arrive. Each second they experience appears to stretch on your clock. The closer they get, the slower their movement appears to you. Eventually the fall looks almost paused. but the fall is not paused. They have crossed the horizon and continued inside. Your view simply cannot reflect that part of their experience. If you watch them through a telescope, the details follow a predictable pattern. Their approach slows, their image dims. The dimming is due to gravitational redshift. Light emitted or reflected from their body or their cabin loses energy climbing out of the gravitational well. At first, the redshift is subtle. Colours appear warmer or slightly muted. Over time, the wavelengths become longer than the eye can detect. The person appears dimmer, then faint, then nearly invisible. Eventually, the light stretches into wavelengths far outside the visible range, then beyond the range of any instrument currently built. The object does not vanish suddenly. It fades slowly, steadily, in a way that matches the structure of the gravitational field. During this slow disappearance, their image also becomes distorted. The closer they get to the horizon, the greater the stretching of space-time around them. If they fall feet first, the light from their feet might be more red-shifted than the light from their head. If the fall happens at an angle, one side of their body might dim more quickly. These distortions grow until the person's image appears stretched along the direction of the fall. The effect is part visual, part temporal. Their signals arrive slowly. Their light shifts. Their form stretches. The combination produces an elongated appearance. From your perspective, the fall takes longer and longer. If you kept a clock near you and compared it to the signals coming from them, you would notice that their signals become delayed by greater intervals. You might send a message to them and receive an immediate reply at first. Later, the reply takes longer. Eventually, it becomes so delayed that the correspondence becomes impractical. Then it becomes impossible. The final signals stretch out over longer and longer periods until they fade entirely. Communication failure from your viewpoint doesn't occur because their equipment breaks. It occurs because the curvature prevents the signals from escaping. The signal leaves them normally, but the redshift and delays grow infinitely large at the horizon from your perspective. The last transmission fades exactly the way their image fades. If you mapped their fall with a graph showing their distance from the horizon over time, the graph approaches the horizon asymptotically. It gets closer and closer, but never crosses. The line continues indefinitely without touching the boundary. The visual and mathematical representation of the fall suggests an infinite duration, and yet the fall for the person takes a finite amount of time. The contradiction is only apparent. It reflects the difference in perspective. Now imagine you are not watching with your eyes, but recording the event with instruments that capture light across many wavelengths. In the early part of the fall, you receive a clear signal. The wavelengths remain stable. The intensity remains strong. Later, the wavelengths begin stretching. Visible light shifts toward infrared. Infrared shifts toward microwaves. The pattern continues. If your instruments can detect the stretched wavelengths, you continue receiving the signal until it moves beyond the range of any device. No instrument known today can track signals stretched indefinitely. Eventually, the last detectable wavelength slips outside all known ranges. If you analyze the data, the behavior matches theoretical predictions precisely. The redshift increases without bound. The shape of the fading matches the predictions of general relativity. There is no abrupt break in the data. The signal simply becomes weaker and slower until it disappears into a range you cannot detect. The dimming of their image is also influenced by how the light bends around the black hole. Light paths near the horizon become severely curved. If the person falls directly toward the horizon, part of the light reflecting from them might orbit the black hole briefly before escaping. This can create unusual distortions in how they appear. The black hole's photon sphere, where light can orbit temporarily, creates a region where some photons circle the black hole once or twice before reaching you. This can cause faint, delayed images or distortions that make the person appear to flicker slightly. The effect is subtle. You would need extremely precise instruments to detect it, but the physics allows it. As the person gets extremely close to the horizon, The lensing effect becomes more pronounced. Light that might have passed directly from them to you gets pulled into curved paths. Some of the light never reaches you. Some reaches you only after taking longer paths. The entire distribution shifts. You see less and less of their form as more of the photons fall inward. The time dilation becomes clearer if you imagine sending a stream of pulses from the falling person to you. Early in the fall, the pulses arrive in a steady rhythm. Later, the gaps between pulses grow, the spacing between pulses grows significantly. Eventually, the intervals become so large that the next pulse seems as if it will never arrive. You might wait years for a signal that originally represented a second. But the signal does finally arrive, because the fall from their perspective has already produced it. For you, it simply reaches after an extended delay. The delays continue increasing until the signals no longer enter your detectors. If you wait extremely long, perhaps centuries or millennia, the fall remains in the same apparent position. The light has long since faded. Your instruments pick up nothing more. The physics suggests that the person is still falling, but the signals have become infinitely redshifted from your point of view. The gravitational time dilation ensures their fall is visible for the entire future of the outside universe, fading slowly into nothing. They never appear to cross the horizon. You could zoom in indefinitely and still never see them cross. Your instruments could become arbitrarily powerful and never record the crossing. The horizon remains the ultimate limit. Your view obeys that limit. Nothing faster than light escapes. Nothing slower escapes either. Only the signals emitted just before the crossing arrive, stretched infinitely into the future. Now imagine the fall from your perspective in slow motion. You watch the person approach the horizon. The fall slows, the dimming continues, the stretching continues. If the fall is angled slightly, one side becomes dimmer sooner. If the person spins slightly as they fall, the spin slows in appearance until it seems to stop. All rotational motions appear to freeze. All motions appear to freeze. Their image becomes a faint, stretched, colourless imprint just outside the boundary. At this point, the outside observer's view becomes entirely one-sided. You continue waiting, but you cannot receive new information. The last signal you received, however faint, marks the final moment you can observe from their timeline. Any events they experience afterward never reach you. This is not because they have vanished. It is because the geometry prevents any new signals from reaching you. The same phenomenon applies to any object falling into a black hole. Stars, gas, dust, planets, or spacecraft appear to slow and fade. The process looks identical. From far away, the fall appears incomplete. From inside, the fall continues normally. This perspective also shapes our understanding of black hole growth. If you watch matter falling in, the matter appears to linger near the surface. It doesn't appear to cross. But black holes clearly grow. Their mass increases. Their horizons expand in response to new mass entering. The contradiction is resolved once again by recognizing the difference between what outside observers see and what actually occurs in the falling object's frame. The horizon grows because the added mass increases the curvature of spacetime. Even though the matter appears frozen near the boundary, it has crossed from its own perspective. The mass contributes to the total gravitational field. The horizon expands to match the new conditions. The outside viewer sees a subtle shift in the shape of the shadow, but never sees the matter physically enter. The growth signals arrive through changes in gravitational behaviour rather than through visual confirmation of the fall. This viewpoint also reveals why information appears lost. If you drop an object into a black hole, the object's details become unreachable. You see the fading, you see the stretching, you see the redshift, but you do not see the object complete its fall. The object's internal information becomes hidden behind the horizon. Theories attempt to explain whether the information remains on the horizon, whether it radiates slowly in the form of subtle quantum processes, or whether it becomes encoded in the geometry itself. But observationally, from far away, the object simply fades and becomes unobservable. Even the exact final moments of the fall become irrelevant from your perspective. The fade is slow, predictable, and smooth. You never receive evidence of the crossing. You see only the outside view, which obeys the rules of relativity. If the black hole is spinning, the fall might appear twisted slightly due to the dragging of spacetime. The apparent path might curve, the image might wobble, but the overall pattern remains the same. The slowing remains, the fading remains, the horizon remains an unreachable visual boundary. As your observation continues, the region near the horizon becomes a quiet image. The person's last signals are gone. The fall appears paused. This view reveals why the horizon separates not just space, but observable nature itself. The outside universe follows one path. The inside follows another. Your view remains connected to the outside. Their experience continues inside. When you begin looking closely at what happens to information near a black hole, the whole subject becomes more complicated than anything covered so far. Up to this point, the ideas have been strange but manageable. You fall inward, light behaves differently, time slows depending on who is watching. All of that can be understood with enough patience. But when you reach the question of information, physics starts to run into difficulties that reveal gaps in our understanding. These gaps aren't caused by black holes behaving randomly. They're caused by the fact that two of our best scientific frameworks, general relativity and quantum mechanics, do not agree on something fundamental at the edge of a black hole. Information may sound like an ordinary word, but in physics it has a very specific meaning. Information refers to the details about a physical system that allow you to describe it completely. For example, if you know the arrangement of particles in an object, their orientation, their energy, their momentum, and their other measurable properties, you have the information describing that object. The laws of physics assume that information is conserved. You can transform matter, you can burn it, you can compress it, you can break it apart, but the underlying information does not disappear. It may get scrambled, it may be hard to interpret, but it survives in some form. This principle is essential to quantum mechanics. It forms part of the foundation of how particles evolve over time. The evolution of a quantum system must be reversible. Every state leads to another state, in a way that preserves the total information. You don't need to know every detail, but the universe keeps track of it. This rule works everywhere we know except at the edge of a black hole, where it seems to fail. Consider what happens when you drop something into a black hole. It could be anything: a rock, a spacecraft, a person, a set of documents, a coded message, or even a particle with a specific spin. From the outside perspective, the object appears to approach the horizon and fade. It never crosses visually, but from its own perspective it crosses and falls inward. After crossing, no signals return. The horizon blocks communication. Anything inside becomes unreachable. The object gets stretched, compressed, and eventually destroyed near the singularity. The structure of the object disappears, and with it, the information describing the object also seems to disappear. This disappearance is what makes physics uneasy. General relativity treats the singularity as a region where the curvature becomes infinite. Relativity doesn't track information from objects entering the singularity. The theory doesn't forbid the loss of information, it simply doesn't address it. The horizon acts as a dividing line that hides the interior completely. For relativity, that's not a problem. Relativity doesn't require information to be preserved. Quantum mechanics, however, demands that information must survive. The principle of unitarity requires it. Everything in quantum mechanics rests on the idea that information cannot vanish. Even if a system appears chaotic or irreversibly changed, the evolution is reversible at the fundamental level. Losing information would break that structure. It would require rewriting the laws of quantum physics entirely. This disagreement is what creates the panic in modern physics. You have one theory describing gravity and space, another describing particles and energy. Both work perfectly in their own domains. but when you combine them at the edge of a black hole, they conflict. The conflict is not minor, it's fundamental. It touches the core assumptions of both theories. The disagreement becomes clearer if you imagine dropping something simple into a black hole, a ball with a colour, a temperature, and a specific arrangement of atoms. From the outside, the black hole eventually settles down into a stable state represented by a few parameters: mass, spin, and charge. These are the only things the black hole reveals. This is described by the idea that black holes have no hair. It means that all the details about the objects that fall in vanish from the outside description. The colour of the ball, the pattern of its atoms, the complexity of its structure, all of it disappears behind the horizon. General relativity accepts this without difficulty, but quantum mechanics cannot. The principle of information conservation states that if you know the final state of a system, you should be able to trace backward and recover the initial state. A black hole with only a few parameters cannot encode all the information about the things that fell in. The black hole ends up with far less detail than it needs to obey the laws of quantum mechanics. This is the heart of the information paradox. It is not a problem about matter being destroyed, it's a problem about information being destroyed. If information leaves the universe, then quantum mechanics must be wrong. If information is preserved, then general relativity must be incomplete. Physicists have been wrestling with this tension for decades. The paradox grows even deeper when you consider Hawking radiation. Stephen Hawking proposed that quantum fluctuations near the horizon cause black holes to emit radiation. This radiation makes black holes lose mass over time. Eventually, the black hole shrinks. Over long enough periods, it might evaporate entirely. But if the black hole evaporates completely, where does the information go? The Hawking radiation appears to contain no information about what fell in. It is thermal radiation with random distribution. Nothing in the radiation points to the ball you dropped or the exact details of its structure. If the black hole evaporates fully, the information seems permanently erased. This outcome would violate quantum principles. It would mean that physical information is not conserved. The universe would have to be described by non-unitary evolution. Every equation in quantum mechanics that assumes reversible evolution would need to be rewritten. This is why the paradox matters so much. It challenges the consistency of the deepest laws of physics. Physicists have proposed many ideas to resolve the paradox. One idea is that the information might somehow be encoded in the Hawking radiation. Even though the radiation appears random, perhaps in subtle correlations between the emitted particles, the information could be preserved. This would require the radiation to be far more structured than it appears. Some theories support this view, suggesting that the radiation is not truly random, but extremely scrambled in a way that still respects quantum rules. Another possibility is that the information is stored on the event horizon itself. This is connected to the idea that the horizon might act like a two-dimensional surface capable of storing data. The concept suggests that every particle falling in leaves an imprint on the horizon. The imprint never leaves. When the black hole radiates energy, the stored information somehow becomes encoded in the radiation so that no information is truly lost. This idea aligns with the holographic principle, which states that everything inside a region of space can be described by information stored on the boundary of that region. The holographic principle emerged partly because of the black hole paradox. The principle suggests that the universe itself might work like a hologram, with the information of three-dimensional space encoded on a two-dimensional surface. Black holes provide strong support for this idea, because their entropy is proportional to the area of the event horizon, not its volume. This is unusual. Most physical systems store information in the volume they occupy. Black holes store information on the surface area instead. This surface-based storage hints that the horizon might be a kind of information layer. There is also the proposal that the singularity might behave differently from the traditional picture. In classical relativity, the singularity is a point of infinite density, but quantum mechanics might prevent such a point from forming. Perhaps the matter inside black holes becomes extremely compressed, but never reaches infinite density. If quantum effects modify the structure inside, maybe information is stored in a stable interior region instead of being destroyed. Other theories suggest that information never enters the black hole in the way we think. Perhaps the horizon reflects information in a subtle way. Some proposals imply that information might remain at the horizon instead of passing through it. The idea is that the horizon may act like a membrane with physical properties. This membrane could interact with matter in a way that encodes details without letting anything truly pass unrecorded. More speculative proposals suggest that black holes might be connected to other regions of spacetime. Wormholes or bridges might exist in some models. Information might pass through these bridges and reappear elsewhere. These ideas are highly theoretical and face difficulties, but they demonstrate how far-reaching the consequences of the paradox have become. The magnitude of the disagreement between quantum mechanics and relativity becomes clearer when you consider how other fields respond to the paradox. Quantum field theory assumes that time evolution preserves information. The paradox challenges that. Thermodynamics deals with entropy. Black hole entropy does not follow ordinary patterns. Statistical mechanics deals with microscopic states. But in black holes, the number of microscopic states suggested by entropy seems impossible to reconcile with the simplicity of the macroscopic description. All these conflicts point toward the need for a deeper theory that unifies gravity and quantum mechanics. This is why physicists call the paradox one of the most important puzzles in modern science. It is not simply a curiosity about black holes, it is a stress test for the entire framework of physics. If the paradox is resolved one way, our understanding of quantum mechanics changes. If it is resolved another way, our understanding of gravity changes. Either outcome requires rewriting some part of what we consider fundamental. Despite the weight of the paradox, the environment near the horizon remains calm for someone falling in. The panic belongs to the equations, not to the traveller. You do not sense the conflict between the theories. You do not feel any disruption in the flow of time or the behaviour of light. You continue falling inward. The difference arises in how the theories interpret what happens to what you're carrying, what you're made of, and what information defines your structure. From the perspective of someone far away, the paradox looks even more dramatic. They see you fade and freeze at the horizon. They see your signals stretch into invisibility. They see the black hole take in mass but lose almost all detail. They see the black hole radiate energy slowly. They see no sign of the information ever returning. The outside view contains all the components of the paradox: the disappearance of the object's details, the evaporation through Hawking radiation, and the apparent loss of information. This mismatch between what goes in and what comes out is the core problem. If information is lost, physics must change. If information is preserved in some hidden way, our understanding of the horizon must change. The fall continues inside regardless of the outcome. When the information paradox first appeared, most physicists expected that some future theory would eventually solve it in a simple and elegant way. The hope was that a deeper understanding of quantum gravity would keep the smooth interior of the black hole, preserve the calmness at the event horizon, and find a way to encode information without changing the basic experience of falling through the boundary. Over time, though, the situation became more complicated. Attempts to preserve the principles of quantum mechanics, while also accepting the predictions of relativity, pushed theories into uncomfortable corners. Those corners led to proposals that challenged the most basic assumptions about what a falling observer should experience. Among these proposals, the idea of a firewall is one of the most dramatic. The firewall concept begins with the idea that quantum entanglement plays a key role in black hole evaporation. Hawking radiation emerges from interactions near the horizon. According to the original calculation, pairs of particles appear, with one particle escaping outward and the other falling inward. The escaping particle forms part of the Hawking radiation. The falling particle becomes part of the black hole. For the radiation to be thermal, the escaping particle must be entangled with its partner inside. Entanglement connects their quantum states, but as the black hole evaporates and releases more and more radiation, the radiation outside begins carrying accumulated information about the black hole's history. Quantum mechanics requires that the outgoing radiation be entangled with earlier radiation if information is to escape in any meaningful way, but entanglement cannot be shared freely. A quantum system cannot be fully entangled with two separate partners at the same time. This limit is known as monogamy of entanglement. A particle cannot maintain perfect entanglement with both its internal partner and the earlier radiation. This is where the tension arises. For the radiation to carry information, the new particle must be entangled with the older radiation. But for the radiation to remain thermal, the new particle must be entangled with its partner inside the horizon. Both cannot be true at the same time. This conflict sets the stage for the Firewall proposal. According to this idea, the entanglement between the outgoing particle and the interior breakdowns. If the entanglement is broken, then the smooth interior predicted by general relativity cannot remain. Instead, the horizon would transform into a region filled with high-energy quanta. These quanta would form a barrier, a firewall, that destroys anything falling into the black hole. The Firewall proposal keeps quantum mechanics consistent. It preserves information by forcing the entanglement to reconfigure, but it does so at the cost of breaking the smooth geometry at the horizon. The falling observer would encounter a violent environment at the boundary instead of a calm transition. This scenario contradicts one of the most central assumptions of relativity, known as the equivalence principle. The equivalence principle states that a freely falling observer should not experience anything unusual at the horizon. If spacetime is smooth, the horizon should be indistinguishable from any other region of empty space. But the Firewall idea violates this completely. It replaces the calmness at the horizon with an abrupt, destructive surface. This contradiction is why the Firewall is so controversial. It supports information preservation, but breaks the geometric assumptions at the core of relativity. The debate became more intense as different groups of physicists pointed out the conflict. If you accept that the horizon remains smooth, then information appears to be lost. If you accept that information must be preserved, then the horizon becomes dangerous. If you reject the danger, then something else in quantum mechanics must change. The theoretical pressure keeps building. None of the options resolve the paradox cleanly without sacrificing something important. To understand the structure of the Firewall idea more precisely, imagine falling toward a black hole with complete confidence that the horizon is calm. You expect that nothing unusual will happen at the boundary. You expect that the curvature remains smooth, that the fall continues normally, and that the tidal forces only become significant deeper inside. But if the Firewall exists, that expectation is wrong. As you approach the horizon, you encounter a region filled with high-energy particles. These particles are produced by the breakdown of entanglement. They have enough energy to destroy anything crossing the boundary instantly. The horizon becomes a destructive layer rather than a smooth transition. This possibility leads to significant conflict. Most physicists believe the equivalence principle must hold. They have tested the principle in many environments, and it has never failed. But the Firewall proposal directly violates it. The only way to avoid the Firewall is to find another resolution to the paradox. The search for such resolutions has produced a wide range of ideas. One idea suggests that entanglement between the interior and the outgoing radiation changes in a subtle way that avoids contradictions. Perhaps the entanglement reorganizes before the conflict arises. Another idea suggests that spacetime geometry around the horizon responds dynamically to the state of the radiation, allowing a transition that preserves smoothness without violating quantum rules. These proposals remain under investigation, and none have been accepted as definitive. Another theoretical option involves modifying the interior of the black hole so that the information is not lost, but is stored in a way that avoids violating quantum mechanics. These ideas often invoke quantum gravity, which has not yet been fully developed. Some theories suggest that the singularity never forms in the classical sense. If quantum effects prevent the singularity from forming, the interior might become a region where information is stored safely. The information could remain in a stable form instead of being destroyed. This would avoid the need for a firewall, but it would require revising the structure of the interior significantly. Another possibility involves the event horizon itself. Some proposals treat the horizon as a physical surface with microscopic degrees of freedom. These degrees of freedom might store information. When the black hole radiates energy, the information could be released slowly through these surface interactions. This idea suggests that the horizon behaves like a thin layer rather than an empty boundary. The layer could hold a record of everything that falls in. This approach supports the idea that the horizon's surface area corresponds to its entropy. There is also the idea of non-local interactions. Non-locality is a concept where physical influences extend across distances without travelling through space in the usual sense. Quantum mechanics includes certain non-local features. Some theorists propose that similar non-local mechanisms might allow information to escape the black hole without violating relativity in a classical sense. These mechanisms would allow the outgoing radiation to carry information despite originating near the horizon. This would avoid the need for a firewall by letting entanglement shift in a controlled, consistent way. Some models suggest that black holes might have a second interior region, often described using complex spacetime geometries. These geometries might connect different parts of spacetime. Information falling into one region might reappear elsewhere. These proposals often involve wormholes. A wormhole could provide a path for information to move out of the black hole without contradicting relativity. But wormholes require exotic matter and energy conditions. They remain speculative. Even more speculative ideas suggest that black holes might not form horizons in the traditional sense. Instead, they might form long-lived states that resemble black holes, but allow information to escape slowly. These states could mimic black holes for extremely long periods before releasing accumulated information. Such a scenario would eliminate the need for a firewall because the horizon would not be a permanent boundary. Other proposals explore the possibility that the black hole interior is not part of our spacetime in the usual sense. Perhaps the interior is linked to other dimensions. If information falls into these dimensions, it may not be lost but simply inaccessible from the outside. This idea fits within certain theories of quantum gravity or string theory, where extra dimensions are possible. But these ideas remain far from experimental verification. Some researchers examine how quantum fields behave near the horizon. They propose changes in the vacuum state that could preserve information while keeping the interior smooth. These changes might subtly adjust how particles behave near the boundary. If the vacuum state is altered, then the entanglement structure might avoid the conflict that creates the firewall. This solution attempts to preserve both quantum mechanics and relativity while avoiding extreme physical consequences. The firewall proposal has motivated many new studies. Its initial shock value pushed researchers toward alternative solutions. Its existence forced the community to examine assumptions about the horizon more deeply. Even if the firewall does not exist, the idea has been useful. It clarified the nature of the paradox and highlighted the importance of entanglement. It also encouraged the search for a more complete theory. Despite the theoretical difficulties, the experience of falling into a black hole remains the same from the viewpoint of the traveller. The horizon feels smooth. The interior remains calm at first. The tidal forces grow slowly. Nothing dramatic occurs at the boundary. The conflict belongs to the equations, not to the falling observer. If firewalls exist, then the experience changes, but there is no experimental evidence for them. So the classical description of smooth falling remains the most accepted picture for now. The firewall paradox also reveals that theoretical physics often explores uncomfortable ideas. These ideas push the boundaries of what we understand. The proposals sometimes involve extreme consequences because the theories they reconcile are incompatible. Black holes force physics to confront the limits of both quantum mechanics and relativity. The The tension between them becomes more pronounced near the horizon. The firewall is one possible outcome of that tension. As you follow the story inward, the paradox shows why black holes remain one of the most important subjects in theoretical physics. They bring together gravity, quantum mechanics, thermodynamics, and information theory. Each field offers its own perspective. The horizon becomes the place where these perspectives collide. The firewall proposal is only one part of the picture. Other theoretical nightmares involve how the interior might behave if quantum mechanics modifies the structure. Some theories predict that space-time near the centre changes in unexpected ways. Others propose that quantum fluctuations could become significant enough to alter the geometry. These possibilities create a wide range of scenarios for what might happen inside. None of them involve the calm, predictable curvature that relativity describes. Even though these ideas remain speculative, they serve an important role. They highlight the need for a unified theory of quantum gravity. Without such a theory, the conflict between relativity and quantum mechanics continues. The firewall paradox is a signal that our current understanding is incomplete. It motivates research in string theory, loop quantum gravity, quantum information, and related fields. These fields explore different aspects of the paradox. String theory suggests that information might be preserved through extended objects rather than point particles. Loop quantum gravity explores how space-time itself might become quantized, which could alter the structure of the horizon. Quantum information theory explores how entanglement behaves in extreme environments. Each approach offers potential solutions, but none have been confirmed. As you continue falling inward, the theoretical conflicts remain outside the range of your personal experience. The interior remains controlled by curvature. The theories attempt to describe what happens at the deepest layers of the interior, but the fall continues smoothly for the traveller. The horizon remains unremarkable. The theoretical nightmares remain mathematical rather than physical in the immediate sense. When physicists first started studying the properties of black holes in detail, they expected that the interior would contain most of the important information. The assumption was simple. If something falls in, the details remain inside, hidden but still present in some form. The horizon would be nothing more than a boundary telling you which region is accessible and which region is not. But as more work was done, especially on the subject of entropy and thermodynamics, the focus began to shift. It turned out that the surface of the horizon seemed to carry more significance than anyone expected. The area of the horizon, not the volume inside, appeared to determine the number of possible internal states of a black hole. This was confusing at first, because almost everything else in physics ties entropy to volume. A gas in a box involves internal states throughout the entire space. A material's entropy depends on how many microscopic configurations exist within it. But black holes broke this pattern. The realization began with calculations showing that the entropy of a black hole is proportional to the area of its horizon. This idea was first proposed through theoretical work connecting gravity and thermodynamics. If a black hole has entropy, then it must have a temperature. If it has temperature, then it can radiate. Hawking later showed how this radiation arises from quantum fields near the horizon. The radiation behaves like heat. The entropy, meanwhile, behaves as if the horizon area counts the number of internal states. This relationship suggested that the horizon is not just a passive boundary. It might store information or represent physical degrees of freedom. This conclusion seemed unusual because it contradicted the normal expectation that information is stored in volume. But the more physicists looked at the entropy of black holes, the clearer the pattern became. The entropy grew with area, not with volume. This suggested that the interior might not contain independent degrees of freedom beyond those encoded on the horizon. If true, the horizon would function like a surface that holds all the information about what lies inside. That idea eventually became part of what is now called the holographic principle. The holographic principle states that the information contained within a region of space can be represented entirely on the boundary of that region. In other words, the universe might work in such a way that all the details inside can be encoded on a surface surrounding them. The principle takes inspiration from holograms, where a two-dimensional sheet encodes a full three-dimensional image. The key idea in physics is that the boundary can carry enough information to describe the interior fully. If this is true for black holes, it might also be true for other regions of space-time. The idea became more serious when researchers studied systems in quantum field theory and found analogies between certain types of gravitational theories and quantum systems without gravity. One of the most influential examples connected a gravity theory in a higher dimensional space with a quantum field theory in a lower dimensional space. The mathematics matched so well that the idea of holography gained significant support. It did not prove that the universe is holographic, but it showed that holographic models can accurately describe complex physical systems. Studying the horizon with this perspective changes how you think about the black hole interior. Instead of picturing space inside as containing countless independent points that each carry their own degrees of freedom, the holographic approach suggests a different structure. It implies that the interior might be a kind of emergent region. Its structure might arise from the degrees of freedom on the horizon. This means that what happens inside is not independent of the surface. Instead, the surface encodes everything necessary to describe the inside. This idea helps address the information paradox. If information about anything falling into the black hole becomes encoded on the horizon, then it never truly disappears. It might become scrambled beyond recognition, but it survives as part of the horizon's microscopic states. Over time, as the black hole radiates, the information could slowly leak out through subtle correlations in the radiation. The process would be incredibly slow and difficult to detect, but it would preserve the fundamental principles of quantum mechanics. The holographic principle allows for information preservation without needing a firewall or a dramatic change to the experience of falling through the horizon. The surface-based entropy also explains why the horizon area grows when matter falls in. If an object enters, the horizon stretches to accommodate the extra information. The increase in area corresponds to the added internal states. The horizon's growth reflects how much additional information the black hole must be able to encode. This fits neatly with the idea that the horizon carries the degrees of freedom. The interior changes accordingly, but the surface is the physical marker of how much information the black hole contains. When you think about falling into a black hole from this perspective, your experience remains unchanged. You don't feel anything unusual as you cross the horizon. But from the outside world, the horizon responds to your entry. It grows slightly. It adjusts its structure so that all the information associated with you becomes stored at the boundary. The interior continues to hold its own structure from your point of view, but the gravitational description from the outside relies on the surface. The holographic principle also provides a way to understand how the interior might appear smooth, while still storing information at the boundary. The smoothness of the interior is part of the classical description. The horizon's ability to encode information is part of the quantum description. These two perspectives overlap if the horizon acts like a storage layer, and the interior emerges from that stored information. This allows relativity and quantum mechanics to coexist more comfortably. It doesn't solve every aspect of the paradox, but it reduces the tension significantly. Another implication of the holographic idea is that different observers might see the same information encoded in different ways. A falling observer might interpret the interior structure as normal space with smooth geometry. A distant observer might interpret the same structure as encoded on the horizon. Both descriptions could be correct for their own reference frames. This duality resembles how quantum field theories describe the same physical situation in different ways depending on the perspective. The idea is that the interior and the surface are two ways of representing one physical system. In this approach, the horizon functions like a type of boundary between descriptions. It separates the region where classical geometry is a useful interpretation from the region where quantum descriptions dominate. If you treat the horizon as a storage system, the interior can behave smoothly without requiring new particles or destructive phenomena. The encoding at the horizon becomes a link between the two frameworks. This view has additional support from studies of how quantum entanglement creates spatial structure in certain models. In some theoretical systems, the amount of entanglement between different parts of a quantum system determines the shape of the emergent space. If entanglement decreases in certain ways, the geometry of the emergent space changes. These ideas connect closely with black holes because the boundary degrees of freedom might generate the interior geometry through patterns of entanglement. This suggests that the structure of spacetime inside the horizon might reflect the quantum structure of the horizon itself. Understanding the holographic principle also provides insight into why the horizon behaves thermodynamically. If the horizon carries degrees of freedom similar to those in other thermodynamic systems, then entropy makes sense, temperature makes sense, Hawking radiation makes sense. The natural connection between horizon area and information hints that the horizon is not an empty boundary but a dynamic surface that interacts with quantum fields. The principle also suggests that black holes are among the most efficient information storage systems possible. They store the maximum allowed amount of information for their size. Nothing else stores information so compactly. This limit aligns with the holographic idea because the horizon area sets the upper bound on how much information can be encoded. Some researchers interpret this as a sign that holography might be a general feature of spacetime, not just black holes. Looking at the horizon as a holographic surface also helps explain why the black hole shadow appears the way it does. The shadow we observe is influenced by the photon orbits near the horizon. These orbits are shaped by the curvature produced by the stored information. The surface encodes the gravitational structure that defines these orbits. This means that the appearance of the shadow already reflects the information stored on the horizon. The observable image connects to the hidden structure indirectly, through the geometry shaped by the encoded information. This interpretation does not require the interior to be empty or non-existent. Instead, it suggests that the interior might be a convenient way to describe effects emerging from the horizon. Different theories take different approaches to this idea. Some treat the interior as real but emergent. Others treat the interior as a representation of certain quantum degrees of freedom. Others treat it as a dual description of the same underlying physics. In all of these approaches, the horizon remains central. One reason the holographic idea became so important is that it allows quantum mechanics and relativity to operate without direct conflict. Relativity needs the horizon to be smooth. Quantum mechanics needs information to be preserved. The holographic principle allows the horizon to be a storage system while still being a smooth surface from the viewpoint of a falling observer. This dual role helps maintain both principles. It doesn't eliminate every difficulty, but it prevents the kind of contradictions that led to the firewall problem. The holographic idea also influences how physicists think about the universe as a whole. If black holes follow the holographic principle, perhaps the entire universe does as well. Perhaps the universe can be described by information stored on a cosmic boundary. This idea remains speculative, but it has gained support through models that reproduce gravitational behavior using lower-dimensional quantum theories. These models provide a consistent, mathematically complete way to study gravity without requiring a full theory of quantum gravity. If the universe is holographic in some way, then the three-dimensional space we experience might emerge from two-dimensional information. This doesn't mean that the universe is an illusion. It means that the structure of space could result from underlying quantum relationships. The geometry we perceive might be a representation of deeper information stored in a more compact form. The holographic idea helps explain why certain gravitational systems behave in ways that match predictions from quantum theories in fewer dimensions. These ideas do not change your personal experience if you fall toward a black hole. You don't see the information reorganizing itself at the horizon. You don't feel the encoding process. You don't notice the surface storing the details of your structure. You simply fall through what appears to be ordinary space. The interior seems smooth at first. The tidal forces only become significant deeper inside. Everything remains calm until the curvature becomes too strong. The horizon plays its role quietly. From the outside observer's viewpoint, the holographic principle offers a way to interpret what happens during the fall. The horizon grows, the surface adjusts, the information becomes part of the boundary degrees of freedom. The interior description continues to exist for the falling observer, but becomes unnecessary for the outside description. The horizon contains what the outside observer needs to know. This perspective helps explain why the horizon area must increase whenever something falls in. The surface absorbs information. The increase in area reflects that absorption. The holographic principle ensures that both entropy and information remain consistent with quantum mechanics. The black hole remains a thermodynamic system with clear rules. Once the horizon has been crossed, the view from the outside no longer matters. Nothing emitted from the interior reaches out again. The region beyond the boundary becomes disconnected from the rest of the universe. From the viewpoint of someone falling in, though, the journey continues. There is no sudden change. There is no sense of arriving at a new category of space. The path ahead remains guided by the structure of curvature. The interior feels like a continuation of everything leading up to it. The smoothness of entry ensures that nothing signals the transition. The physics at this point becomes difficult because the details of what lies beyond the horizon depend on theories that have not been unified. General relativity predicts one structure. Quantum mechanics suggests that something different may occur. Without a unified theory, the interior remains a subject where speculation fills in the gaps left by incomplete frameworks. The simplest interpretation based on classical relativity states that after crossing the horizon, everything continues falling inward along unavoidable paths toward the center. The singularity appears in the equations as the point where curvature becomes infinite. The interior shapes all motion toward that point. Spacetime funnels everything inward. The distances shrink in all directions except for the one along which the stretching continues. The deeper the fall, the stronger the tidal forces become. This picture describes the interior as a region dominated by increasing curvature. It suggests that nothing can stop the approach toward the central point, where density becomes unbounded. This classical description does not include quantum effects. It does not include the information paradox. It does not include holographic ideas. It remains a clean but incomplete model. If relativity were the only theory needed, the interior would be straightforward. The geometry would compress everything toward the center. The stretching forces would intensify. Structures would break apart. The inward path would lead to a single endpoint. The story would end there. But relativity does not account for quantum mechanics. At extremely small scales, quantum effects become important. They cannot be ignored. The interior of a black hole reaches conditions where both extreme curvature and quantum rules apply simultaneously. Neither theory works fully under these conditions. This is where speculation becomes necessary. Physicists explore possibilities because the existing theories cannot describe everything consistently. One of the most common questions is whether the singularity truly exists. In relativity, the singularity is a location where the equations break down. It is not necessarily a physical object. It marks the limit of the theory's reliability. Many researchers believe that quantum mechanics must alter the structure of the singularity. Quantum effects might limit the density of matter. They might prevent spacetime from collapsing into a true point. They might create a core where quantum gravity dominates. This would produce a region where known physics changes significantly. The exact structure remains unknown because no complete theory of quantum gravity exists. One possibility is that the interior becomes a region of extremely high but finite density. Instead of a true singularity, matter might condense into a state where quantum repulsion prevents further collapse. This idea appears in some approaches to quantum gravity. It suggests that the interior could resemble a dense core. The structure of spacetime around such a core would differ from the classical picture. The curvature might remain high but avoid becoming infinite. This would help resolve certain theoretical problems, but it requires assumptions about quantum gravity that have not yet been confirmed. Another idea is that space-time inside a black hole might connect to another region entirely. The interior could lead to another part of the universe, or even another universe. This idea appears in some theoretical solutions involving wormholes or extended space-time geometries. These solutions allow interior paths that avoid singularities and continue into new regions, but these solutions depend on conditions rarely met in the physical universe. They require exotic matter or specific symmetries that may not exist. Still, the possibility remains part of the conversation because nothing in the known laws strictly forbids extended geometries. They simply have not been observed. Even without exotic extensions, the interior might behave differently than expected because of quantum effects near the horizon. If the holographic principle holds, then the interior could be an emergent region. This means the interior space might arise from the quantum information encoded on the horizon. If this is true, the interior would not exist independently of the horizon. Instead, it would be created through relationships among the quantum states on the surface. In this view, falling inside does not require a physical structure sitting underneath the horizon. The experience of space inside emerges from the encoded data. This allows the interior to feel real to the falling observer, even if the description from outside never requires it to exist independently. This idea becomes easier to explore when considering how entanglement shapes emergent geometry in certain theoretical models. If entanglement patterns determine the shape of space, then the interior might reflect those patterns. The curvature, the tidal forces, and the path toward the center might be manifestations of deeper quantum relationships. The classical description of the interior would then be a large-scale approximation of the more fundamental quantum structure. This does not change the experience of falling in. The geometry feels real and continuous. But the underlying interpretation becomes different. Some theories propose that the interior is real, but time behaves differently inside. According to these ideas, the interior could contain regions where time slows, stops, or behaves in unexpected ways due to quantum interactions. This changes how space-time evolves as you fall in. It might prolong the fall. It might alter the nature of the stretching. It might create new layers of structure near the center. But without experimental data, these scenarios remain speculative. The equations provide possibilities. The physical universe provides no direct measurements. Another approach suggests that the interior might not be a region of continuous space. Instead, it might consist of discrete units governed by quantum rules. This idea appears in theories where space-time itself becomes quantized. In these models, space-time is composed of small units that follow quantum laws. At large scales, these units form smooth geometry. At small scales, the geometry breaks into individual elements. Near the singularity, the discrete nature of space-time might prevent infinite curvature. The classical prediction of infinite density could be replaced by a quantum limit. This would produce a boundary inside where classical physics fails, but quantum physics remains consistent. There are also models proposing that the interior could behave like a type of condensed state of space-time. In these models, the curvature reaches a saturation point. Beyond that point, space-time changes its structure. Instead of collapsing further, it transforms into a new phase. This new phase might have properties very different from the familiar structure of space. It might compress information in new ways. It might create boundaries within the interior. It might alter the path toward the center. Some theories propose that the information falling into a black hole remains intact, but becomes distributed throughout the interior in non-local ways. This means that instead of being compressed into smaller regions, information spreads across the entire interior. This distribution prevents singular collapse. The interior becomes a region where information spreads through non-local quantum interactions. This would help preserve information while avoiding infinite curvature, but it requires assumptions about non-locality that are difficult to verify. Another speculation involves the idea that the singularity might bounce. In some quantum cosmology models, when matter reaches extremely high density, it triggers a bounce that reverses the collapse. This is similar to some proposals for the early universe. If the interior behaves this way, then falling matter might eventually reach a point where the inward collapse halts and reverses. The bounce could produce an expanding region of spacetime on the other side. Some researchers suggest that this could connect black holes to other universes or to regions of this universe that develop later in time. These ideas remain speculative and depend on assumptions about quantum gravity that are not yet confirmed. Despite the wide range of possibilities, the experience of falling inside does not depend on the fine details of speculative models. For a long portion of the fall, the behavior remains governed by classical curvature. You continue moving inward. The tidal forces increase. The interior feels smooth at first. The deeper structures remain hidden behind layers of curvature. You follow the path dictated by spacetime without sensing the speculative details that theorists explore. As the fall continues, the tidal forces intensify. The curvature grows stronger. Structures deform more rapidly. The interior gradually becomes a region where physical stresses exceed the limits of any known materials. The process remains governed by relativity until the scale becomes small enough for quantum effects to matter. The transition to the quantum regime occurs at extremely small distances. At that point, the classical prediction of a singularity becomes unreliable. The quantum structure takes over, but its exact nature is uncertain. Some theories propose that the interior becomes a region dominated by quantum pressure. This pressure could counteract collapse and create a stable core. The core might resemble a highly compressed object. Its structure might depend on unknown physical laws. It might interact with the surrounding space-time in unusual ways. But the falling observer would reach conditions where no material or biological structure can survive. The curvature would be too strong. The stretching would be too extreme. The interior would not provide a stable environment for complex structures. Other theories suggest that the interior might effectively vanish as an independent region. According to these ideas, the interior might not exist as a separate space. Instead, it could be a mathematical construct used in the classical description. The true physical degrees of freedom might reside entirely on the horizon. The interior experience would be valid for the falling observer, because relativity provides the appropriate description for their frame. But from a deeper quantum perspective, the interior might not be a fundamental part of the universe. It might be a representation of the information encoded on the horizon. This duality is common in holographic theories. The interior exists from the viewpoint of the falling observer. The horizon encodes the necessary details from the viewpoint of the outside observer. Both descriptions are valid. They do not conflict because they belong to different reference frames. The interior experience does not require the horizon to behave as a physical boundary in the classical sense. It requires only that the geometry provide the appropriate paths. Speculating about the interior becomes more challenging when considering interactions between quantum fields and curvature. Quantum fields behave differently in curved space-time. Their energy levels shift. Their vacuum states change. These effects become significant near the horizon, and even more significant inside. The interactions might create new types of particles. They might alter the nature of the singularity. They might modify the curvature. These interactions suggest that the interior could be filled with quantum fluctuations. The fluctuations could play a role in how information is preserved or transformed. Some theoretical models propose that these fluctuations become strong enough to generate a type of effective pressure. This pressure could resist collapse. It could stabilize the interior. It could force matter into a new configuration. But there is no consensus on whether these effects are strong enough to prevent the singularity predicted by relativity. Others suggest that the interior could be governed by a type of quantum foam. In these models, space-time at very small scales is constantly fluctuating. These fluctuations might alter the path toward the singularity. They might break the continuity of space. They might create small loops or bubbles that affect motion. These effects could prevent the classical collapse. but their exact behaviour remains speculative because no direct observations confirm the structure of space-time at such small scales. The interior also becomes a testing ground for ideas about unification. Gravity and quantum mechanics must work together at this scale. Neither theory can be ignored. The quest for a unified theory attempts to describe situations like the interior of a black hole. This means that the interior remains a place where theoretical ideas meet their limits. It acts as a training ground for new theories because it forces the existing ideas to confront their inconsistencies. Even though speculation exists, the general behaviour of the fall remains predictable for most of the interior journey. The curvature guides everything inward. The geometry dominates every motion. The stretching intensifies. The interior experience remains smooth at first. The theoretical complexities emerge only at the smallest scales, where no direct measurements exist. The fall eventually leads to a region where classical curvature predicts infinite compression. Quantum effects must intervene. The nature of that intervention remains unknown. Whether the interior becomes a dense core, a quantum region, an extended geometry, or something entirely unexpected remains a subject of active research. What matters is that the interior reveals the limits of our understanding. The question of whether a black hole ever truly ends might seem straightforward, especially after learning that black holes can emit radiation. At first glance, the idea that something which traps light and matter could slowly shrink and eventually disappear feels like a contradiction. The concept becomes even more confusing when considering how gently the radiation is produced. Nothing dramatic occurs at the horizon. Nothing erupts outward. Nothing breaks the calmness of the surface. Instead, the black hole loses mass through a process so slow that it barely changes over ordinary timescales. Understanding how this gradual loss works helps explain what might happen in the long term. It also raises more questions than it answers, because the evaporation process interacts directly with the information problem and the structure of space-time. The mechanism behind black hole radiation comes from combining quantum field theory with the curved space-time around the horizon. Vacuum fluctuations continually produce pairs of particles in empty space. These fluctuations occur everywhere. Normally the particles annihilate quickly and return their energy to the vacuum. Near the horizon of a black hole, however, the geometry complicates this behaviour. When a pair forms, one particle can fall inward, while the other escapes outward. The escaped particle becomes part of Hawking radiation. The particle that falls inward effectively carries negative energy relative to the outside universe. This negative energy reduces the black hole's mass. The radiation itself appears thermal. It resembles heat emitted from a warm object, but the temperature of this radiation depends on the size of the black hole. Large black holes emit radiation extremely slowly. Their temperature is far below the cosmic microwave background. This means they absorb far more energy from the universe than they emit. They grow rather than shrink. Only after the universe cools significantly would these black holes begin to lose more energy than they gain. Small black holes, on the other hand, emit radiation more quickly. Their temperature is higher. They lose mass faster. This size dependence creates a long-term evolution, where large black holes grow at first. Over extremely long timescales, they may eventually begin to lose mass once the universe becomes cold enough. When this happens, the radiation slowly removes energy from the black hole. The loss of mass causes the horizon to shrink. The shrinking increases the temperature. The increased temperature speeds up the radiation. This process continues until the black hole reaches a size where the radiation becomes very rapid. The final stages occur quickly relative to the earlier stages, but still extremely slowly compared to human timescales. For a typical supermassive black hole, the evaporation process would take far longer than the current age of the universe. Even for smaller black holes, the timescales remain huge. Only hypothetical microscopic black holes would evaporate within measurable times. None have been observed. As a result, the evaporation of black holes remains a theoretical prediction without direct observational evidence. Still, the physics behind Hawking radiation is widely accepted because it follows from established principles. The long-term disappearance of a black hole raises a new set of questions. The most important is what happens to the information carried by everything that fell in. The radiation appears random. It carries no details about the objects that entered the black hole. If the radiation remains random until the final stages, and if the black hole disappears completely, then the information appears lost. This contradicts quantum mechanics. The long goodbye becomes part of the information paradox because the outgoing radiation seems unable to preserve the information. Some theories propose that the radiation eventually carries the information through subtle quantum correlations. These correlations would not appear in the early stages. Only after enough radiation has escaped would the outgoing particles begin reflecting the information encoded at the horizon. This idea suggests that information remains stored on the horizon throughout most of the black hole's existence. Only near the middle and later stages does it begin to leak out. The horizon gradually releases the stored details. This process requires a long delay between the object falling in and the information reappearing. Other theories suggest that the information might remain encoded in a remnant. A remnant would be a leftover object once the black hole has shrunk to a very small size. The remnant would carry the information rather than releasing it. This avoids losing information but introduces new challenges. If remnants store information, they must have extremely high storage capacity. They must also remain stable. The existence of remnants creates difficulties in quantum field theory because it allows an enormous number of possible states. The theory would need to account for this. No evidence for remnants exists, but the idea remains a possibility. Another possibility is that the interior stores the information in a way that becomes accessible only through quantum gravitational effects. These effects might prevent complete evaporation. They might transform the final state into something that still contains the information. But without a complete theory of quantum gravity, these ideas remain speculative. The long-term evolution of black holes depends on physical laws not yet fully understood. The fate of the horizon itself also depends on these unresolved issues. If the horizon encodes information through microscopic degrees of freedom, then the evaporation process must release that information. The area of the horizon decreases as radiation escapes. The decrease in area corresponds to a decrease in the number of internal states. These states must transfer their information to the radiation for quantum mechanics to remain consistent. The details of how this transfer occurs remain unknown. Some proposals suggest that the structure of the radiation changes as the black hole shrinks. Others suggest that the interior becomes linked to the radiation in complicated ways through quantum entanglement. Hawking radiation remains a smooth process. It does not disturb the horizon from the perspective of an observer falling in. The radiation is barely noticeable near the horizon. A falling observer does not feel heat or pressure. The radiation occurs from the viewpoint of an outside observer. The difference in perspectives creates another layer of difficulty when analysing the evaporation process. The horizon behaves differently depending on the reference frame. For the outside universe, the horizon shrinks. For the falling observer, the interior remains consistent. These two views must reconcile within a complete theory. The long-term weakening of the black hole also affects the behaviour of objects falling in over time. In the early lifetime of a black hole, the horizon expands with each new addition of mass. The growth of the horizon corresponds to the increase in entropy. In the later lifetime, the horizon shrinks. The curvature changes slowly. The interior region becomes smaller. The paths available to falling objects change. But these changes occur over immense timescales. No object falls in long enough to witness the horizon shrinking significantly. The evaporation process continues until the black hole reaches extremely small size. At this stage, quantum gravitational effects dominate. The classical description breaks down. The radiation becomes intense. The energy output becomes large. but the detailed behaviour of these final moments remains unknown. The absence of a complete theory leaves several possibilities open. The black hole might disappear entirely. It might leave a remnant. It might transform into a new state. It might produce an outburst of radiation carrying encoded information. Without observational data, only theoretical descriptions guide our understanding. One way to approach the problem is by studying how entanglement changes during evaporation. The radiation that escapes becomes entangled with the states left behind. As the black hole shrinks, the structure of entanglement must evolve. Eventually, the entanglement between different parts of the radiation becomes strong enough to encode the information that has been stored on the horizon. This idea fits within the holographic principle. It suggests that the interior becomes unnecessary for the outside description. The information is stored at the boundary and released gradually. Another approach connects evaporation to the geometry of spacetime. As the black hole shrinks, the curvature around it changes. The shrinking horizon alters the local geometry. The structure of spacetime near the horizon becomes narrower. The gravitational redshift changes. The region where light can orbit changes. These changes modify how the radiation escapes. The geometry also determines how information might be encoded in the radiation. This geometric approach does not require a specific mechanism for information release. It relies on the idea that the horizon's degrees of freedom gradually influence the radiation. Some theories propose that the final moments of evaporation involve a rapid release of information. According to these ideas, the early radiation remains thermal and carries no information. Only when the black hole is small enough do quantum effects become strong enough to encode information in the outgoing particles. This creates a scenario where the last fraction of the black hole's lifetime carries the bulk of the information. The early stages appear random. The late stages reveal the hidden structure. This scenario avoids losing information while preserving the early predictions of Hawking radiation. Other theories challenge the entire premise of evaporation. They suggest that the radiation might not be exactly thermal. The calculation of Hawking radiation assumes a smooth horizon and a specific vacuum state. If these assumptions change, the radiation might carry information from the start. The radiation would still appear thermal at first glance, but would contain subtle quantum signatures representing the interior. This idea maintains consistency with quantum mechanics without requiring dramatic changes to the horizon or to the interior. It simply modifies the calculation of the radiation. Even with these possibilities, the lifetime of a black hole remains one of the longest processes in the universe. Supermassive black holes would evaporate over time so long that the universe would pass through multiple phases before the process becomes significant. The universe would cool, stars would fade, galaxies would change, black holes would remain long after other structures have transformed. This makes the evaporation process a subject more relevant to theoretical cosmology than to astrophysical observation. The long goodbye also interacts with the expansion of the universe. If the expansion continues indefinitely, the cosmic background temperature will drop. Eventually, it might become low enough for large black holes to begin losing mass. The evaporation process would then begin on cosmic scales. Over even longer times, the black holes would lose significant mass until the final stages arrive. This slow evolution would shape the far future of the universe. If the expansion accelerates, the evaporation process becomes even more isolated. Black holes exist in regions where the cosmic background becomes increasingly cold. Their radiation becomes the last active process in an otherwise quiet universe. The timescales involved extend far beyond any structures currently visible. These ideas highlight the difficulty of understanding the long-term fate of black holes. The process involves quantum mechanics, relativity, cosmology, and thermodynamics. Each field offers insights. None provide a complete picture. The long goodbye becomes a bridge connecting multiple layers of physics. For someone falling into a black hole during its early lifetime, nothing about Hawking radiation affects the experience. The radiation is too weak to influence the fall. The interior remains governed by curvature. The horizon remains smooth. Only on timescales far beyond any journey does the evaporation process matter. The falling observer never reaches the final moments of the black hole's life. The journey ends long before the horizon shrinks to a significant degree. From the outside, however, the evaporation process becomes part of the narrative. The horizon shrinks, the entropy decreases, the information encoded on the surface must leave in some form. The theories attempt to describe how this occurs. None have achieved full agreement. The journey inward through a black hole raises many questions about the nature of space, time, and information, but it also brings you to a place where reflection becomes easier than explanation. After moving through the horizon, exploring how light behaves, understanding how time changes depending on who is observing, and drifting further into regions where both quantum mechanics and relativity struggle to offer clear guidance, the idea of turning your attention back toward the edge creates an interesting contrast. This contrast doesn't come from physically reversing course, because there is no outward path once the horizon has been crossed. Instead, it comes from thinking about how the boundaries shape the experience and how the outside universe becomes a distant presence that continues without you while your own path remains directed inward. Before reaching the horizon, the universe beyond it was visible in full. Stars occupied every direction. Light behaved normally. The changes began slowly. The curve of spacetime bent the appearance of distant objects. The shift from one region to another followed the rules you heard earlier, and the gradual dimming reflected how the access to outside information narrowed as the boundary approached. Once inside, the outer universe faded into a small shrinking fragment of the visual field. Eventually it disappeared completely from reach. The horizon turned from something that looked distant into a location from which no outward communication could escape. When thinking back now from a place deeper inside, the horizon becomes more of a memory than a visible region. You cannot return to it. Nothing moves outward. But the memory remains clear. The transition was gradual. Nothing announced itself. No change in colour or sound indicated that one environment had shifted into another. The fall continued in the same way it had before, only the external signals revealed that the boundary had been crossed. The quietness of the horizon remains one of the most striking features of a black hole, because it separates eras of experience without creating physical sensations for the traveller. Looking outward from this deeper region, you might imagine what the horizon would look like if you could still see it. The picture depends on which observer's viewpoint is used. A distant observer sees the horizon as the boundary of darkness. You faded as you approached it. Your motion slowed from their viewpoint, and your signals stretched until they vanished. In that description, you appear to remain suspended near the horizon forever. But your own experience continued. You passed through the boundary in a finite amount of time. None of the slowing or fading affected your internal rhythm. Your perspective reveals how relative the entire situation is. Thinking back on that contrast also brings into focus why the horizon matters so much to physics. It creates a division between regions that obey different sets of observable rules. The outside observer sees one story, you see another. Both stories reflect the structure of space-time. The horizon marks the point where the two descriptions diverge. Inside, the information about what happens cannot reach the outside. Outside, the fading images do not represent the internal experience. The boundary functions like a limit on communication, not like a wall. Deeper inside the black hole, the curvature increases. The stretching forces that began gently are now more noticeable. The interior guides every motion toward the center. While the horizon created the significant shift in terms of communication and the ability to send signals, the interior creates the significant shift in terms of the forces acting on matter. The geometry continues directing the path inward. But even here, it is possible to reflect on how the horizon framed the earlier parts of the journey. When thinking back to the moment before entering the boundary, the outside universe still felt reachable. Signals still arrived. The stars still provided a reference frame. The curvature had begun distorting their positions, but the overall appearance of the sky remained meaningful. The passage through the boundary removed all of that reference. The interior does not provide outward landmarks. The horizon now exists only as something that once could be seen. The experience becomes a study of how memory interacts with the continuous motion inward. This reflective view also brings up the question of which features of the horizon mattered most. For the traveller, the absence of physical sensations at the boundary stands out. That absence might seem surprising because of the dramatic descriptions often attached to black holes. But relativity predicts that the horizon should feel no different from any other region of empty space. The curvature changes gradually. Only the global structure of space-time creates the horizon. Locally, no physical properties force a response from your senses. This calmness continues to feel unusual as you look back on it, because it contradicts the dramatic nature often associated with black holes. The lack of physical markers at the horizon also helps explain why the interior feels continuous. The space inside does not have a sudden start. It emerges naturally from the geometry outside. The tidal forces grow stronger later, not at the boundary. The fall remains familiar until the curvature becomes extreme. The soft transition from outside to inside becomes easier to appreciate once the path continues far enough to understand how the interior diverges from the exterior over time and distance. Thinking about the long-term behaviour of the black hole adds another layer to this reflection. The horizon that appeared so steady during your fall is not permanent on cosmic timescales. Over unimaginable periods, the horizon shrinks due to Hawking radiation. The long goodbye stretches far beyond any possible experience inside the black hole. But understanding that eventual shrinkage makes the horizon feel less like a fixed boundary and more like a temporary feature of space-time. The interior you moved into exists only for as long as the black hole itself remains. When the black hole evaporates completely in the distant future, the horizon disappears and the interior no longer exists in the same way. This idea is difficult to connect directly with your current fall because your timeline is far shorter than the evaporation process. You crossed the horizon at a moment when the black hole was stable. Its mass barely changed. The radiation it emitted was far too faint to affect your fall. The interior structure matched the classical predictions. But on cosmic scales, the horizon will eventually shrink, and the states encoded on its surface will eventually release their information. The interior you are falling through, and the horizon you passed cannot last forever if evaporation continues as predicted. From your deepening perspective, this raises another interesting thought. The horizon remains invisible now, but the idea that it continues to shrink in the distant future presents a picture where the boundary changes even though you have moved beyond it. The curvature you experience does not respond to that long-term future, because you fall inward on timescales too short to notice such influence. But thinking back to the horizon with the knowledge of evaporation allows you to imagine how the external boundary slowly changes long after your experience has ended. This contrast between personal experience and cosmic evolution reflects the enormous difference in timescales involved. Looking back also highlights how the boundary shaped the way physics describes the fall. All of the major theoretical questions, information loss, the firewall proposal, the holographic principle, and the nature of the interior focus on the horizon. The horizon acts as the dividing point where theoretical frameworks collide. Relativity demands smoothness. Quantum mechanics demands information preservation. Thermodynamics demands entropy be accounted for. These demands converge at the horizon. Your fall moved through the region where those demands must reconcile, and yet you notice none of the conflict. The theories struggle, but the physical experience remains calm. This calmness makes the horizon even more interesting, because it reminds you that the conflict concerns the descriptions of observers, not the direct experience of falling. The horizon marks where the external description stops being able to explain internal events. While the outside world sees a slow approach that lasts indefinitely, the internal experience continues without interruption. The horizon becomes an interpretive boundary rather than a physical one. Considering what lies behind you, even though you cannot turn back, also reveals how the interior creates a different kind of relationship with time. Before crossing, time was shaped by how the distant observer saw your fall. The stretching of time from that viewpoint made your movement appear slow. The internal experience avoided the stretching. The momentum of your fall carried you forward. Inside, time continues based on your own internal rhythm. The outside observer's timeline no longer influences your path. Their universe continues, but it no longer connects with you. This separation emphasizes how time inside the horizon becomes a personal path defined only by the geometry ahead. Thinking about that separation brings up another idea. The horizon acts as a boundary between shared and unshared events. Before crossing, your actions influence and are influenced by external signals. After crossing, nothing you do reaches outward. No new information about your path leaves the interior. The fall becomes an isolated sequence of events. The outside universe continues independently. The two stories no longer interact. This change has no sensation attached to it, but it reshapes the meaning of time and communication. Reflecting on the experience can also help clarify how the interior reshapes understanding. The earlier stages of the journey involved explanations of how light bends, how time stretches, and how matter behaves near strong curvature. These explanations rely on physics that is well understood. As the fall continues inward, the explanations become more theoretical. The classical description begins failing. Quantum mechanics must fill the gaps. But no complete theory exists. This creates a region where speculation helps fill in the unknown details. Looking back from inside makes this situation clearer. The horizon marks not just a physical boundary, but also a boundary between known and unknown physics. The behavior outside and at the horizon can be described confidently. The interior requires assumptions. This difference becomes more meaningful the deeper you travel. You cannot rely on classical theory forever. The deeper you go, the more the theoretical uncertainties influence the interpretation. While the interior continues shaping the path inward, the horizon behind you represents the last region where external descriptions remain certain. Thinking about it from this deeper perspective highlights how the journey has moved from well-understood physics toward regions where understanding becomes less complete. The transition between certainty and speculation parallels the transition from seeing the outside universe to losing contact with it. Both transitions occur gradually. Both transitions create a sense of distance between past understanding and current experience. This distance creates a kind of psychological calm. The further you drift inward, the more the outside universe seems remote. The horizon behind you becomes something that belonged to an earlier stage of experience. The interior shapes everything now. The path forward is defined by geometry. The external universe becomes something you can consider intellectually but cannot interact with. That separation creates an environment where reflection feels natural. The fall continues, but the sense of movement becomes less connected to external reference points. Thinking back even farther, to the time before approaching the black hole adds more context. At that stage, the black hole appeared as a dark region in space with bright matter around it, or with stars behind it. The approach revealed lensing effects. The horizon seemed like the outer surface of the shadow. None of that perspective applies now. Inside, the black hole no longer appears as an object. There is no external shape to view. The interior is simply the region through which you are moving. The horizon no longer appears as a surface. It becomes a conceptual boundary rather than a physical feature. The shift from seeing the black hole to being inside it becomes part of the journey's narrative. The deeper you go, the more the memory of the horizon resembles an earlier point in the journey rather than a physical location. This is because the geometry directs you forward in a way that removes outward direction as a path. The idea of return cannot exist in a physical sense, but thinking about the boundary remains helpful because it represents the last region where external signals functioned. It marked the point where the inside and outside stories diverged. Remembering that helps keep the larger structure of the experience in context. As the curvature grows, the reflection continues in a calm way because nothing about the environment disrupts the steady rhythm of thought. Even the increasing tidal forces remain gradual. They build over time. The stretching effect becomes more noticeable in the deeper regions. But the geometry continues controlling the motion in a predictable way. The focus on reflection does not interrupt the physical process. The fall continues while the mind reviews earlier stages. At this depth, looking back toward the horizon becomes less about the physical boundary and more about understanding how the earlier stages set the direction for everything that followed. The calm passage through the horizon shaped the initial conditions for the interior journey. The fading signals mark the last point of contact with the outside universe. The inner region now guides the remainder of the path. As you settle into this reflection, the inward motion remains steady. The curvature grows sharper. The geometric structure tightens. The path ahead continues to narrow. The environment becomes quieter in a conceptual sense because the outside universe no longer influences anything. The fall deepens. The horizon remains part of the memory of how the journey began, framing the context for the path that continues ahead into regions where the structure of space-time becomes the only guide.